Imagine you're an archaeologist, someone who unearths artifacts to study ancient civilizations and preserve the stories of history. You're excited because you're the first person to explore a new dig site. The rising sun creates a warm glow on the orange and yellow rock of the ancient riverbed in front of you. You forget your early morning tiredness and yesterday's 15-hour flight as you breathe in the crisp, clean air. You pause as you remember the words of your site leader the previous evening. This spot has never been studied, but it's absolutely perfect for preservation. You're guaranteed to find something, and anything we find we'll be able to present at the International Archaeological Research Institute next summer. What could be hidden under that rock? What ancient mysteries will be uncovered? What stories will be unearthed? The possibilities seem endless. Hi there, my name is Rob. I'm a consumer product marketing leader. I work on marketing projects here at Google. And every time I get the opportunity to analyze data, it feels like I could be an archaeologist on the verge of an incredible discovery. Some people see a data sheet or a table of disorganized numbers and they think, ugh, this is so lame. But data professionals know better, don't we? We know that hidden inside the numbers, columns, and rows are golden nuggets of information, never before seen insights or compelling trends. These interesting bits of hidden knowledge are stories waiting to be shared, and stories are one of the most impactful ways to communicate ideas. The amazing truth for us data professionals is that all data has stories to tell. So whether you're an aspiring data professional or you want to learn to tell a good story, preferably both, welcome to this course. By now, you have a fairly good idea of the scope of this program and the basics of Python coding. Now, it's time to dig deep into unexplored data and try to make sense of it. Are you ready to explore? We will begin with how to find and sculpt stories using a 6-part process called exploratory data analysis. Then, we'll discuss how PACE applies to telling stories using data. Do you remember the data professional workflow acronym PACE? That is, plan, analyze, construct, and execute. We'll talk about how PACE applies to exploring data and learn about the necessity of visualizations in understanding the data. Finally, I'll show you how to perform exploratory data analysis on a data set in Python, expanding on those Python skills you learned previously. Later in this course, you'll learn about data sources, data types, data structuring, and data cleaning. Using Python notebooks, we'll discuss how to work with missing values, outliers, and categorical data. We'll talk about the ethics of exploring and cleaning raw data, and how to communicate your questions and findings to various audiences. Later in this course, you'll learn more about the visual analytics platform, Tableau. We'll talk about how to enhance your data story with visuals and presentations. Along the way, I'll share tips on shaping your data stories for different audiences, like how to build data visualizations that target an audience's needs. Data professionals at Google identify the essential skills that are fundamental to working in data. Throughout this course, there will be opportunities to practice finding and telling stories with data. In short, stories can change lives. And data-driven stories are particularly compelling because they are based in numbers. They can also communicate principles, concepts, cautions, and new ideas to others. To give you an example from my own life, I actually started my career as a data analyst for a healthcare consulting firm. I was responsible for identifying and recommending the most effective treatments for patients with serious medical conditions ranging from asthma to diabetes to cancer. To develop my recommendations, I analyzed the medical records of millions of patients and compared and contrasted the outcomes, side effects, and medical costs of each treatment. Through my findings, we were able to recommend treatments that would not only help these patients heal, but also help improve their quality of life and reduce their medical bills. The stories are out there, just waiting to be found. So get out your shovels and magnifying glasses and let's start exploring. Hello again. Welcome to the first section of this course. In the next few lessons, we'll be exploring the foundations of data analysis and how the 6 practices of exploratory data analysis help us find and tell stories using data. We'll begin by discussing each of the 6 practices of exploratory data analysis. You'll learn about what they are and why they're important. Then, we'll learn about how our data professional workflow, PACE, or plan, analyze, construct, and execute, fits into the process of exploratory data analysis. Finally, you'll learn the importance of data visualizations in the data exploration process. We'll consider what data visualizations are and how data professionals use them to learn about and share data. The next few lessons will lay the foundation for how to tell stories using data. I hope you're as excited as I am to get started. Imagine you work for a company that's been hired to clean out a very old, one-room warehouse full of antiques. Your manager says no one has used the building for decades and doesn't know what the owners used it for over the years. You've been assigned to clean it out and create a detailed inventory of what you find inside so that the items can be sold at auction. The manager suspects there'll be interesting antiques inside. Since many items are covered by blankets, you don't know what the room contains. You start cleaning from one side of the room to the other, and you keep a digital inventory of the items you find. As you explore, you find a pile of metal gears, chains, and connection parts of all different sizes and shapes. You count them and write metal parts 47. You also find 5 large metal sheets, 12 large tricycles, and 7 metal poles, among other things. As you write these new items, you start to wonder if they're related or not. This simple example demonstrates how data professionals explore data and learn more about the stories and trends along the way. As you uncover and clean up what is in front of you, the individual parts and pieces within the data will start to tell a larger story. Of course, data requires a few extra techniques and practices than in the warehouse example, but the general idea is the same. You'll need to make sense of raw data content by reordering, categorizing, and reshaping it. You'll find a lot of different terms in the world for this process. Data wrangling, data remediation, data munging, and data cleaning are all the most common. We combine all of these practices into a familiar term that most data professionals are familiar with, exploratory data analysis, or EDA. Exploratory data analysis, or EDA, is the process of investigating, organizing, and analyzing data sets and summarizing their main characteristics, often employing data wrangling and visualization methods. The 6 main practices of EDA are discovering, structuring, cleaning, joining, validating, and presenting. These practices do not necessarily have to go in this order, and depending on the needs of the data team and the type of data they study, they may perform EDA in different ways. You'll also find that often the EDA process is iterative, which means you'll go through the 6 practices multiple times in no particular order to prepare the data for further use. Let's spend time on each of the 6 practices so that you have a better idea of what I mean. Discovering is typically EDA's first practice. During this practice, data professionals familiarize themselves with the data so they can start conceptualizing how to use it. They review the data and ask questions about it. During this phase, data professionals may ask, what are the column headers and what do they mean? How many total data points are there? In the example of the old warehouse at the beginning of the video, the discovering practice might involve walking through the room and removing coverings to get an idea of the amount and types of items. After some initial discovering, the next step is to start organizing. This EDA practice is called structuring. Structuring is the process of taking raw data and organizing or transforming it to be more easily visualized, explained, or modeled. Structuring refers to categorizing and organizing data columns based on the data already in the data set. In terms of the calendar data, for example, it might look like categorizing data into months or quarters rather than years. From the old warehouse analogy, structuring could be categorizing the items into metal and non-metal categories and getting a total count for each type. Before we move to the next practice of EDA, let's take a moment to talk about bias. Bias, in the context of data structuring, is organizing data in groupings, categories, or variables that don't accurately represent the whole data set. Most experts would agree that eliminating all bias from how data is structured is almost impossible because each person's individual ideas, training, and experiences are different. As professionals, however, it's important to try to avoid bias while structuring data. For example, imagine you want to know what percent of the population has a college degree in the UK, but your model data only contains London residents. The data would be considered biased until you add data from the rest of the UK. In our warehouse example, trying to avoid bias might involve remaining flexible with the categories, potentially creating new categories as you uncover more and more items. The next EDA practice is data cleaning. Cleaning is the process of removing errors that may distort your data or make it less useful. Missing values, misspellings, duplicate entries, or extreme outliers are all fairly common issues that need to be addressed during the dataset cleaning. In the warehouse example, you might decide to put broken or unusable items in a separate box away from other items. We'll move to another practice called joining. Joining is the process of augmenting or adjusting data by adding values from other data sets. In other words, you might add more value or context to the data by adding more information from other data sources. For example, you might find during the discovering, structuring, or cleaning processes that the dataset doesn't have enough data for you to complete a specific project. In that case, you should enrich the data by adding more to it. As an example, remember when I talked about the UK and college degrees to help understand bias? In that instance, joining would be adding the data from the rest of the UK rather than just including data on London residents. Going back to our warehouse analogy, imagine a museum manager sorts through the items and gives you the dates of when each was made. The information from the museum manager acts as a different group of data you can join with your own as you inventory the items. Next on the list of EDA practices is validating. Validating refers to the process of verifying that the data is consistent and high quality. Validating data is the process for checking for misspellings and inconsistent number or date formats, and checking that the data cleaning process didn't introduce more errors. Data professionals typically use digital tools such as R, JavaScript, or Python to check for inconsistencies and errors in a data set and its data types. As for our warehouse analogy, validating could be like using the museum manager's knowledge to get an idea of how old the items are. The last EDA practice is presenting. Presenting involves making your cleaned dataset or data visualizations available to others for analysis or further modeling. In other words, presenting practice is sharing what you've learned through EDA and asking for feedback, whether in the form of a clean dataset or data visualization. We will be using the term data visualization a lot. To be clear, a data visualization is a graph, chart, diagram, or dashboard that is created as a representation of information. You might think that presenting always comes at the end of the EDA process. However, presenting can come at any point in EDA. Data visualizations aren't exclusive to the presenting practice. They should be used throughout EDA. They help you understand data and point out trends and insights to others. In the warehouse analogy, presenting could mean showing your manager the progress on the warehouse and how many different items were found. In the workplace, as a data professional, presenting might look like preparing visuals and a slide presentation to share with your team. As you begin to plan your presentation, you should consider people with visual or auditory impairments by providing robust descriptions of the data. You can use things like alt text, descriptive text, or captioned recording of the data so that your audience can explore the data themselves. We will cover each of the EDA practices in detail later on, but one of the most important things to learn about the process is to ensure your EDA work does not misrepresent the data itself. The story you uncover should come from the data, not from your mind or biases in the data. It is your duty to convey your data in both an ethical and accessible way. Consider the warehouse analogy. To ensure you communicate your data ethically, you should give an accurate count of the materials and not overestimate the quantities of the antiques. In the workplace, communicating data ethically would be presenting sales numbers in context, year over year, so that rises and falls don't appear exaggerated in data visualizations. Once you complete the warehouse project, you realize you've uncovered a story. You find a dusty pair of signs that advertise food for sale. Suddenly, the items you found start to make sense as a whole. These antiques appear to be a collection of supplies used by a group of traveling food vendors. Now, how about that for discovering a story? Of course, you should confirm this information using historical records before sharing. Have you ever walked into a room to grab a specific item and then become distracted and forget why you were there? As data professionals, our curiosity and excitement for finding stories in data might cause us to forget the original purpose for our data exploration. Obviously, we want to maintain our natural curiosity, but most importantly, we want to focus that curiosity on what questions need to be answered or what problems need to be solved. We seek a balanced mindset, one of targeted curiosity. This balance can be achieved by using PACE. As you learned, PACE, or plan, analyze, construct, and execute, is the workflow some data professionals use to remain focused on the end goal of any given data set. Imagine you work for a multinational company that manufactures office equipment. The finance department asks you to use the last 10 years of data to predict sales for the next 6 months. How might you approach your EDA of the data given this task? In this video, you'll learn to combine PACE and EDA practices. Remember, EDA stands for exploratory data analysis. You might think that because analysis is in its name, that EDA falls only in the analyze part of the PACE workflow. The truth is, EDA applies to every part of PACE. You'll find the 6 practices of EDA all intersect with the other parts of PACE. Discovering, for example, is in line with the planning part of PACE, and presenting can be a major part of the executing part of PACE. As you will learn, data professionals don't just find and tell any random story from the data. Data insights are guided by a project's purpose and goals. The plan may come from a stakeholder or manager. You can think of it as the project plan or the stated goal of the company. For example, let's consider the sales prediction from the office equipment company earlier in the video. As you recall, your task is to predict the next 6 months of sales performance based on 10 years of sales data. When you start your EDA, you realize the data sets you've been given contain a lot more data than you need. It would benefit you and your company to extract only the columns you need to predict sales, which would be date of sale, item, price, and sales rep, for a total of 4 columns. While cleaning, joining, and validating, you can exclude data on material cost, item ID numbers, database cost center numbers, and vendor names. Cleaning 10 years of data sets with 4 columns is much more manageable than 8 columns. Of course, in a typical workplace, it shouldn't surprise you that after you've done a lot of the work to complete your EDA based on the plan, the finance department says they actually wanted the predicted profit margin, not the sales targets. Miscommunication happens in every workplace, even in data analysis. If stakeholders, engineers, and data specialists are not clear on the plan, the results won't tell a cohesive or effective story. Instead, the results will likely lead to confusion, disagreement, and wasted time. One example of good communication would be sharing the PACE plan with anyone who might be involved. Another example could be sharing the analysis with a working group to get feedback before sharing the analysis more broadly. And finally, it's important to understand stakeholders' most important goals for the company before presenting them. We will address details about communication strategies in upcoming videos. The point is, when you have a data set in front of you, remind yourself of the reasons for your analysis. Once again, consider the office equipment company. You've been given 2 data sets, one with transaction ID number and date, the other with transaction ID number and total cost. You're asked to forecast the next 6 months' sales numbers. If you consider the purpose of this task, what is something you might do with the 2 data sets? You might consider the EDA joining practice and include all data from the two data sets together, transaction ID, date, and total cost. For another example, let's say you have a hospital's data on treatments performed over the last year. If the goal is to prepare data to make a purchase order for the materials and supplies for the upcoming year, what type of EDA might you consider? It would be a good idea to start by using the EDA practice of structuring to group the data by the type of items needed for each treatment. Data professionals are set up for success when they follow a framework like PACE. When a professional applies that framework to the way they perform the 6 practices of EDA, they keep priorities in order and they focus on achieving the project's purpose. Of course, as data professionals, our first priority is to accurately represent the data itself. If your company's project plan does not align with what the data is telling you, it is your responsibility to communicate that to stakeholders. Let me return to the sales forecast request at the office equipment company. Imagine you're given data on sales revenue specific from 2 geographic regions, but stakeholders are requesting a global forecast. As a data professional, it is your responsibility to ask for globally representative data to complete the task. Working with data from only 2 regions would be inadequate to make a global projection. Timelines, stakeholder pressure, or client needs should never cause a data professional to bypass what is required by the data. Misrepresentation of data is never warranted. Let's review. Data professionals should strive to align their work with the plan part of PACE. Keeping the focus on PACE helps determine the most effective ways to perform EDA practices while maintaining ethical representations of data. Coming up, we'll explore how PACE can help guide the development of data visualizations. I'll meet you there. Let's review a scenario, shall we? You're given a giant table of numbers and a data visualization. Which would you choose to most quickly communicate data insights? Data visualizations are far more effective at quickly communicating complex information than data tables. Now, let's consider how this relates to EDA. Data visualizations are important tools that data professionals use to tell stories with data throughout their workflow, particularly the EDA practice of presenting. Plotting parts or all of your data set on a bar graph, a scatter plot, a pie chart, or a histogram will help you and others to understand the data no matter where you are in the EDA process. As a data professional, you won't be working with simple, clean data sets that have only a few hundred lines of data. You'll be working with data frames that have thousands or hundreds of thousands of data points spanning months, years, or decades even. The more data you have, the more visualizations you'll need to create to understand how each variable impacts the other. When you start looking at new data, a popular and valuable tactic is to visualize it, like time series data on line charts to understand periodicity or scatter plots to get a good idea of data distribution. Data visualization can also help you explain your data set to stakeholders and other data professionals. It is your job to discover the important points, trends, biases, and stories that need to be shared, then design data visualizations in an effective way for different audiences. For example, imagine you're a data professional who works for an appliance manufacturer. Let's say you perform an analysis for the manufacturing team. During the analysis, you discover a delay in the manufacturing process. You need to communicate these findings to 2 different audiences, the manufacturing supervisors and the executive leadership team. When you share your findings, some stakeholders may not understand the data insights without the help of data visualizations. The ways data visualizations are designed will communicate different messages to stakeholders with vested interest in different parts of the project. For example, the manufacturing supervisors might need to review time series data plotted out over time to identify the manufacturing delays. Meanwhile, the executive leadership team would likely be more interested in financial impact analysis. Those 2 data visualizations would need to be designed differently based on the needs of your audience. We will go into detail on exactly how to do that in the upcoming videos, but in the meantime, understand that the balance of words and data visuals in a presentation impacts the business decisions made from data insights. A carefully prepared data visualization can mean the difference between changing the mind of a stakeholder and the data being ignored. However, visualizations can also cause confusion or even misrepresent the data. For instance, imagine a data professional develops a visualization and changes the scale of the axes, or the ratio of the graph height and width to make the line chart look flat or steep. This example of skewing is the opposite of what data analysis is about. Because you will be the person most familiar with the data and its story, it is essential that your visualizations not mislead your audiences. Returning again to the manufacturing equipment example, if you provide a data visualization showing a sharp increase in sales over the last 6 months, your audience might assume the company is doing very well. But if data from the last 2 years shows the 6-month increase comes right after a long 18-month decline, the last 6 months has a different context. Showing only the last 6 months as opposed to the 2 years is misrepresenting the sales data. Your data-driven storytelling is an opportunity to present facts and visualizations that are ethical, accessible, and representative of the data. Being an ethical presenter of the data you analyze means being honest and very clear about what is and isn't in the data. Along with that, remember to design your data visualizations in a way that is accessible to everyone. For example, avoid pairing red and green in data visualizations, as it can be difficult for people with color blindness to read. Generally, blue and orange are the better choice to use in data visualizations. We'll go into more detail on ethics and accessibility in upcoming videos. In other videos, we'll use digital visualization tools like Tableau and Python packages like matplotlib and Seaborn and plotly to understand how to use your data and graphs and charts in ethical and accessible ways. These tools will be part of your everyday work as a data professional. Remember, creating visualizations about your data sets will help you throughout the entire EDA process. There's often no better tool for telling a good data-driven story than a well-made visualization. We've talked a lot about finding stories within data and about how it is your job to tell those stories to the best of your ability. There is, however, another story weaving its way through the readings, videos, and quizzes, and is still continuing to unfold as you listen to this video. And if it isn't clear, it's the story of you. Coming this far in the program shows you are determined to become a data professional. I hope you feel inspired by the idea of defining not only the stories of your data, but your own story as well. I'm sure you noticed that this part of the course had very little coding instruction in it. That's by design. The job of data professionals is about more than coding and statistical modeling. The first part of the course reflects that. It is also important to recognize how exploratory data analysis, or EDA, applies to finding, sculpting, and telling data-driven stories. If you talk to data professionals in the career space, many will share how beneficial EDA is in day-to-day work. So I took some time to talk about the practices of EDA: discovering, structuring, cleaning, joining, validating, and presenting, and review the value of these practices. We talked about the PACE workflow and how it can apply to EDA in our search for stories within the data. You also learned about the ethics of working with data and the importance of representing data accurately when we tell data stories. Lastly, you learned how data visualizations are essential for understanding, forming, and presenting data-driven stories. You learned that telling a data-driven story that accurately represents the data and is inclusive of its audience is an example of exceptional data analysis. The story doesn't end here, though. We have many more concepts to learn in this course, including using Python tools and coding blocks to help you in your EDA practices of discovering, structuring, and cleaning raw data sets. In this program, you will work with data sets that represent the type of raw data you'll likely see every day in your career as a data professional. Remember, all data have stories to tell. These stories are often hidden well, and it will take an especially curious and determined professional to discover them. The data-driven stories you'll be discovering have the potential to change an entire company, or even the world. I am looking forward to continuing our journey together through the rest of this course as you discover questions, solve problems, and learn new concepts. I hope with each new concept you learn, you discover a little more about your own story as well. I'll see you soon. Have you ever tried to explain something to a friend that you didn't understand very well? Maybe it was a difficult math assignment, a complex news story, or the way a family member cooks a favorite dish. When you're trying to teach a topic you're not an expert on, it can be challenging to explain the details and give clear instructions. As a data professional, you never want to be in this position with the data you analyze. In fact, your goal should be to know your data very well. When you're reviewing a table of data, it's important to understand where the data is from, what the column headers mean, what the data will be used for, what the imperfections are, and the small details in between. Making sense of raw data is why we're here. Welcome. I'm excited for you to build on the knowledge that you've learned so far to perform exploratory data analysis, or EDA, on the kind of data sets you'll see on the job. You'll start by learning about the many different data types and data sources that you will encounter in your work and how to study them. After that, you will return to those Python notebooks to start coding the concepts you've learned. We'll also go into more details on the first two practices of EDA, discovering and structuring. While learning about the discovering practice, we will use popular Python functions to get to know the information contained in the datasets. You'll learn to use different visualization techniques to uncover hidden correlations and connections in the data. As for structuring, you will learn to apply Python functions to large datasets for many different operations, including sorting, filtering, extracting, slicing, joining, and indexing large datasets. You'll learn to make basic corrections or formatting improvements to whole data columns or entire datasets. All of these techniques and practices will help you learn about the data and find the story that needs to be told. Along with all the Python functions and coding scripts, we will talk about what to do when questions about the dataset arise that you can't answer, like why there are missing data fields, for example. We'll also make sure the EDA you perform aligns with the PACE workflow that we have set. At its core, this section of the course is about digging through a dataset for the first time and investigating it as meticulously as you can. It is up to you to find the stories in the data. Most data professionals will tell you that comprehensive EDA is the key to useful visualizations and models. If there are questions left unanswered or misunderstandings still present in the data after EDA, any presentation or machine learning model based on it will not be particularly useful. It might feel like trying to explain a math assignment you don't fully understand. Remember, all datasets have stories to tell. Let's get to work and find them. Imagine for a moment you're preparing a meal for friends. You have a recipe and raw ingredients, but this is the first time you'll cook the dish. Of course, you want your friends to enjoy it. If you're like me, the idea of being judged on perfectly preparing a recipe the first time you've made it is scary. Believe it or not, this cooking example is what it's like to be a data professional during the discovery practice in EDA. The recipe you're trying to follow is equivalent to your company's project plan. You have everything you need at your disposal: a kitchen, or a digital workspace with dedicated servers for data analysis computing, raw ingredients, or a data set, and it's up to you on how to best mix, blend, and cook the ingredients in order to make a winning dish that your friends will enjoy. In this video, let's focus on raw ingredients. As a data professional, you will be handling all kinds of different data in a number of different formats and file types. I will share with you the most common data sources, data formats, data types, and a few Python functions. Once you're familiar with the dataset source, format, and the data types within it, you'll be ready to handle questions or challenges as they arise during the analysis. First, when you're given data, you'll want to know the source. The term data source can have many different meanings in different contexts, but for our purposes, we'll be defining data source as the location where the data originates. One good thing to know about a data source is how and when to contact subject matter experts such as engineers or database owners. These are the people who either generated the data or are in charge of delivering the data sets. When you have questions about the data as you do your discovery, they will be the ones you reach out to. Knowing the ownership and source of the data is critical because by understanding the data source and who is responsible for it, you can determine its reliability. Does the data owner have experience collecting and storing data? Does the data owner have any financial stake in the data's output? Understanding the source of the data will help you in telling the story of the data and make ethical decisions about its use. Another important part of determining the data source is understanding how it was collected. Whether the data was collected through a report from a computer system, a custom selection from a large online database, or a data table that has been manually entered, knowing about how the data was gathered will help you understand questions that may come up during EDA. For example, missing values could mean many different things. Maybe the database owners either didn't know or didn't want to disclose the data for manual entry, or there might be lagging data or a system bug from an online database. The next thing you'll need to know about your data sources is the data file format. The main data formats you'll experience as a data professional are tabular files, XML files, CSV or comma-separated value files, spreadsheets, database files, or JSON files, which stands for JavaScript Object Notation. Here are a few examples of what these file types look like. If you've gotten this far into the program, you'll be familiar with tabular and Excel files by now. As you know, they organize data in tables with data variables organized by rows and columns. Rows representing the objects and columns representing aspects of the objects in the dataset. The advantage of this file type is a clear identification of patterns between variables. CSV files are a simple text file which can be easy to import or store in other softwares, platforms, and databases. They look like rows of text and numbers separated by commas or other separators. The rows of data are broken up by commas rather than strict columns. The advantage of CSV files is more from a computer science aspect in that it is really a file type which is easily read, even in a text editor. It is also easy to create and manipulate. In Python, you can use the read CSV function to read, write, and work with tabular data that is in the CSV format. Database, or DB for short, is another way of storing data, often in tables, indexes, or fields. Database files are great for searching and storage. They often require some basic knowledge of search query language, or SQL. We will explore how to query data from databases in an upcoming section. Lastly, JSON files are data storage files that are saved in a JavaScript format. You'll find the information in these files better resembles Python code, but with different language, function, and format. JSON files may contain nested objects within them. You can think of nested objects as expandable file folders or drop-down menus within the code itself. For example, a JSON file might have the ingredients for a recipe listed, and under each ingredient, you would have included nested information like weight, calories, and price as objects that define the ingredients. There are a few advantages of JSON files. They have a small message size, they're readable by almost any programming language, and they help coders easily distinguish between strings and numbers. There are Python libraries and functions built for working with JSON files. As you learned previously, you can import the JSON Python module into your Python notebook to use as an encoder and decoder of JSON files. There are also tools in the pandas called read.json and to.json, which will translate JSON files and convert an object to JSON format type, respectively. As a data professional, you may also be tasked to find data stories in other formats like HTML, audio files, photos, email text, images, or text files. In every case, there are Python libraries or functions that can help you discover and structure the data for your research project. There's no best format for the data. It will depend on the project and storage type. You're just looking for the format that best fits that particular data set. Finally, the last raw ingredient in understanding data is types of data. You may already be familiar with the many different categories of data. As a reminder, there is a first, second, and third-party data. First-party data is data that was gathered from inside your own organization. Second-party data is data that was gathered outside your organization, but directly from the original source. Finally, there's third-party data, which is data gathered outside your organization and aggregated. Knowing the types of data, whether first, second, or third party, will help you be able to more efficiently answer or seek answers to the questions you may have that arise during analysis. For example, if there are missing values in first-party data, then someone in your organization can help you determine whether the missing data can be recovered. For third-party data, you'll likely have to reach out to a separate organization. You'll also be familiar with different types of data, like geographic, demographic, numeric, time-based, financial, and qualitative data. Your job as a data professional will require that you understand and work with all these types of data. Knowing the data source, format, and type you're working with will help you to answer two very important questions. First, given what you know of the data so far, does it align with the plan as defined by your PACE workflow? And second, do you have enough data to follow through with the plan in the PACE workflow? If you've answered either of these questions with a no or not sure, it is your job to reach out to the owners of the data and project stakeholders to inform them of the issue you found. For example, let's say you're assigned to predict the number of customers a retailer will expect to see next month. Unfortunately, you're only given profit margin data and only 2 months worth of customer purchase data. Because the profit margin data won't help you with returning customers and only 2 months of data won't give you much confidence in prediction, you should go back to the data source. You'll need customer purchase data from the last few years to accurately predict an upcoming month. Returning to the data source and requesting more data will keep everyone in the process, including you, focused on the plan that was established as part of your PACE workflow. When you're working as a data professional, keeping this focus will be essential in identifying and carrying out high priority and value add tasks. As a data professional, you're expected to know what the data means and how to work with it to find solutions to business problems, like cooking a meal. You'll be given the tools and ingredients you need to work on the problem. It is up to you to work with your team if there aren't enough ingredients or if what you've been given won't make a great dish. Now that you have a better understanding of exploratory data analysis and why it's important, let's do some discovering on a dataset similar to one you might work with in your career as a data professional. The National Oceanic and Atmospheric Administration, or NOAA, keeps a daily record of lightning strikes across much of North America. Let's imagine we've been tasked with performing EDA on this dataset so that it can be used to predict future lightning strikes in this region. In this video, we will use Python to do the EDA practice of discovering on data gathered by the NOAA in 2018. we will talk through the first steps data professionals will typically do when encountering a dataset for the first time. Let's open up a Jupyter Python notebook to begin. First, we'll want to import the dataset we wish to analyze and the applicable Python libraries we want to use. This preparation step is similar to the way a painter gathers paintbrushes, paints, and an easel before they start painting. Similarly, we want to collect all our tools and data. The NOAA dataset we will use is in the public domain, but we have provided a file to download so you can follow along. To begin, import the Python libraries and packages you plan to use. In our case, we'll use pandas, numpy, and matplotlib.pyplot. To save time and increase efficiency, rename each library or package with a two-letter abbreviation, PD, NP, and PLT, DT, respectively. Another quick tip for saving time, instead of clicking Run Cell, you can always use the keyboard shortcut Control or Command Enter. You may recall that Python packages like pandas and numpy are open source code packages that have been pre-designed and coded to help analyze and manipulate data more efficiently. pyplot is a package focused on plotting charts and visualizations. Most data professionals import all their commonly used libraries, packages, and modules at the beginning of any coding session, but you can import them at any time while working with data in a Python notebook. The pandas conversion function to date-time is incredibly helpful when working with dates and times. We will first convert our date column to date-time, which will split up the date objects into separate data points of year, month, and date. This is good practice because throughout your career, you'll be grouping data by various time segments. We'll get to that later. After running these initial functions, you are ready to begin your EDA discovering practice with this dataset. Let's begin with the head method or function. Head will return as many rows of data as you input in the argument field. We'll look first at the top 10 rows. When I input head with a 10 in the argument field and click Run, the first 10 rows of the dataset are now in our notebook. This dataset contains 3 columns of data: date, number of strikes, and center point geom. At this point in the exercise, we will need to clearly understand what each of these columns means. Date and number of strikes are fairly straightforward. You'll want to pay attention to any dates and their format, which in this case is year, month, date. You'll also find when looking at the date column that lightning strike data is recorded almost every day for at least one location in the year 2018. Some column headers are obvious, but some, like the column header center point geom, aren't. If you are not sure about what the column headers mean while you're working on a project, you could go back to the public documentation available from the NOAA to confirm its meaning. For this video, the information is provided. The center point geom column refers to the longitude and latitude of the recorded strikes. We know the number of columns, but we also want to know how many rows of data we'll be working with. Another great EDA discovering tool is the info function. The method called info gives the total number and data types of individual entries. Keep in mind that data types are called dtypes in pandas. If we type df.info into our notebook and run it, we will get this output. Our range index tells us our total number of entries, nearly 3.5 million. We also find that the data values in our date and center point geom columns are classified as objects, and the data in our number of strikes data column is classified as int64. Int64 refers to integer 64. It means that the data type contains integers or numbers between 2 to the power of negative and positive 63. Simply put, int64 is a standard integer somewhere between negative 9 quintillion and positive 9 quintillion. There is one more D type you might see when performing the info function, str, which refers to a string. Like objects, you'll likely be familiar with strings already. Strings are a sequence of characters or integers that are unchangeable. Getting back to the data set, we have a pretty good idea about its size and scope. We know it has 3 columns, and we know it has 3,401,012 rows. We know what the columns mean. There are other methods or functions that we could use during our practice for discovering. For example, the methods describe, sample, size, and shape are all useful for learning about a data set. For this data set, though, we have what we need in order to understand what is going on in the data set from a discovery standpoint. So next, let's determine which months have the most lightning strikes by plotting our first visualization. Remember, your data set has over 3 million rows. If we don't do any categorizing or grouping, we could end up with a notebook that is stuck endlessly trying to run the code. We've already converted our date column to date time, which makes it easy for us to manipulate the data in the column. We'll want to group our daily strikes into something more manageable, like months, for example. So let's make our date reference the number each month corresponds to in a year. That is, January is 1, February is 2, and so on. We'll do that by creating the column month using the code dfdate.dt.month. dt in this instance stands for date time. Next, we'll make it easier to interpret on a chart. Let's convert the month data, which are currently numbers, to month name abbreviations. We'll do this by creating another column, month underscore text. This code will take the string of characters or month names and slice to include only the first 3 letters. Before we try to plot this data on a chart, we need to sum the numbers of strikes in all locations by month. We can do this by creating a data frame using the group by function, in which we will include the columns month and month text, because these are the columns we will use to group and order the lightning strikes. We'll use the sum function to add the lightning strikes for each month together. For our last lines of code in this video, let's plot the number of strikes by month for the year 2018 into a bar chart, and then total number of strikes by state on a map. This will help us get a good sense of the data story. You'll find that this looks like a big block of code, but because we are using the matplotlib.pyplot, the actual code for the visualization is not too difficult to follow. First, we have the plt.bar function, which will have us enter the data columns we wish to plot with x-axis first, month underscore txt, followed by height or y-axis, which we will fill in with number underscore of underscore strikes. Next, we will give the bars a legend or label, as it's called in Python, which we will input as number of strikes. Lastly, we'll fill in our bar graph details with the x and y axes labels and the visualization title. Leave the legend and show argument field blank for now. After we run the code, you'll see that August 2018 had the most lightning strikes, while November and December 2018 had the least amount of strikes. Lastly, it's helpful to plot the count of strikes per state on a map. We can do that in Python with a package called plotly.express, which we will import as px. Use the CSV file provided for the remainder of this video. To help us with lightning strikes by state, we'll create a column called dfCountByState, where we group the data by state code and a sum of the count lightning column. Next, we'll use the fig equals px.coropleth function to create a United States map visualization. As part of the function, we'll first tell Python which column to use for the information, which will be the one we just created, df count by state. As part of the choropleth function, we have locations, color, hover name, and location mode, which we will populate with the data state code, count, lightning, state code, and USA states, respectively. The last bits of code are just updates to the layout with title text and geoscope, which will populate with state rankings. Use the function fig.show and click Run. This renders a graphic of color-coded lightning strike counts by state. Now, you've completed your first experience coding for an EDA practice in Python. Very well done. We have a lot more to talk about, and this is a great start. I've often found that stepping away from a challenging project and taking a break helps me find new perspectives on my work. I like to get a can of seltzer from the fridge, take a walk, and reflect on what I know and what I don't know about the project I'm working on. The EDA discovering process requires a similar shift in perspective. After I perform an initial discovering of a dataset, I've usually learned enough about the project to make a hypothesis based on that data. A hypothesis is a theory or an explanation based on evidence that is not yet proved true. Data professionals often use hypotheses as a starting point for continued investigation or testing. Once I've formed my hypothesis, I'm in a better position to discover more about the data and achieve my ultimate goal, telling a story. So far in this course, we've discussed how to begin the discovering practice of EDA. You learned how to examine data sources, data formats, and data types. You've considered column header information and averages, and you've made some initial visualizations to represent your data. You use Python to determine the size and scope of the dataset, and learned when you need to ask the owner of the data clarifying questions. After you've made sense of the raw data, you're ready for the next step of the discovering process, drafting a list of questions and forming a hypothesis. In this video, you'll learn how to ask meaningful questions about the goal you've outlined in the PACE workflow to better understand what is missing from your dataset and what you still need to find out. One way I like to do this is by breaking the original problem into smaller chunks. Some questions you might ask include, how can I break this data into smaller groups so I can understand it better? How can I prove my hypothesis? Or, in its current form, can this data give me the answers I need? Let's consider these questions in context. For example, imagine you work as a data analyst for an international airline and you need to determine whether lowering the prices of tickets will attract more customers in certain days of the week. To solve this problem, you might ask, which months have the most passenger traffic? Which weeks, dates, or known holidays have the highest number of passengers? When are tickets typically purchased? Then you'd form your hypothesis. In this case, your hypothesis might be, I predict that Tuesdays and Wednesdays of a normal business week have the fewest number of passengers and flights. So, if the airline lowers prices for Tuesdays and Wednesdays during non-holiday weeks, then they will sell more tickets. Eventually, you would test your hypothesis by analyzing the data to understand whether the airline would attract more customers by lowering the prices on those specific flights. The purpose of asking questions and forming a hypothesis is to better understand what you want to learn from the data and what the results of your testing might show. Later, when you're performing other practices of EDA, you can refer to these questions and your hypothesis to determine whether you've supported or refuted your original theory. To answer the questions and test the hypothesis you or your team formed, you will need a plan. For instance, you might need to contact the subject matter expert who owns the database or is more familiar with the data source. Or you may need to do your own research. In other words, leave no stone unturned. It's an old saying about an ancient Greek legend, and it means to search everything you can to think of to find what you're looking for. If you discover that your search for answers only brings more questions, that's a good thing. You're eliminating the possibility of misinterpreting or misrepresenting the data each time you learn more. At some point, you may need to decide you need to organize or alter the data to find the answers to your questions. For example, You may need to regroup entries into months or years rather than days or weeks. Or you might want to group customer ages into age ranges to help you understand trends more effectively. Sometimes combining or splitting data columns will be necessary for creating models to answer questions. Other times, changing date formats or time zones in time-bound data may be all that's required. For example, in your work with the international airline, you were tasked with finding days to enact lower ticket prices so the airline could attract new passengers. Imagine the data you were given listed ticket prices in US dollars, but the original request was to lower ticket prices for passengers departing from Europe. One change you would need to make immediately is to convert US dollars to euros. Making small changes to your data, like formatting the time, changing a unit, or converting the currency, is all part of the discovering process. However, with every change you make, stay focused on the problem you're assigned or the plan that you established as part of the PACE framework. As we discussed, every dataset is different. Asking questions and forming a hypothesis will take time and effort, but ultimately, answering questions and testing your hypotheses will be the way you find the stories hidden in your data. If you get stuck, it might help to step away from your initial discovering work and think through your questions and hypotheses again. Any visualization rendered, conversion made, questions answered, or hypothesis tested must be true to that dataset's story. Who knows? Maybe you'll find the answer on your walk break. And wouldn't that be refreshing? As a data professional, you can expect to work with date-time objects and date strings. In this video, we'll continue coding in Python and practice converting, manipulating, and grouping data. By the end of this video, we'll create a widely used data visualization, a bar graph that tells a story with your data. Working with date strings will often require breaking them down into smaller pieces. Breaking date strings into days, months, and years allows you to group and order the other data in different ways so that you can analyze it. Manipulating date and time strings is a foundational skill in EDA. In this video, you will learn to convert date strings in the NOAA Lightning Strike dataset into date-time objects. We will discuss how to combine these data objects into different groups by segments of time, such as quarters and weeks. Let's open a Python notebook, and I'll show you what I mean. Let's begin by importing Python libraries and packages. To start, import matplotlib and pandas, which you've used before. To review, pyplot is a very helpful package for creating visualizations like bar, line, and pie charts. Pandas is one of the more popular packages in data science because its specific focus is a series of functions and commands that help you work with data sets. The last package, Seaborn, may be new to you. Seaborn is a visualization library that is easier to use and produces nicer looking charts. For this video, we'll use the NOAA Lightning Strike data for the years 2016, 2017, and 2018 to group lightning strikes by different time frames. This will help us understand total lightning strikes by week and quarter. As I mentioned at the beginning of this video, when manipulating date strings, the best thing to do is to break down the date information like day, month, and year into parts. This allows us to group the data into any time series grouping we want. Luckily, there's an easy way to do that, which is to create a datetime object. Now, as you'll recall from a previous video, this NOAA dataset has 3 columns, giving us the date, number of lightning strikes, and latitude and longitude of the strike. For us to manipulate the date column and its data, we'll first need to convert it into a date-time data type. We do that by simply coding dfdate and making that equal to pd.toDateTime with dfdate input in parentheses. Doing this conversion gives us the quickest and most direct path to manipulating the date string in the date column, which currently is in the format of a 4-digit year, followed by a dash, then the 2-digit month, a dash, and lastly, the 2-digit day. Okay, this is the exciting part. Because our dates are converted into pandas datetime objects, we can create any sort of date grouping we want. Let's say, for example, we want to group the lightning strike data by both week and quarter. All we would need to do is create some new columns. You'll see here we're creating 4 new columns: week, month, quarter, and year. With the first line of code, we're creating a column week by taking the data in the date column and using the function strf time. This function from the datetime package formats our datetime data into new strings. In this case, we want the year followed by a dash and the number of weeks out of 52. If we want that string, we need to code it as $y dash w $v. The %sign is the command which tells the datetime format to use the year data in the string. The W implies this is a week, and the V stands for value, as in a sequential number running from 1 to 52. The final string output for the column data will be in this format: 2016-W27. The next line of code gives us the new month column. The argument is then written as $y dash $m. This will output the 4-digit year followed by a dash, then the 2-digit month. Essentially, we're removing the last 2-digit date from the original date string. Next, we will create a column for quarters. In this case, a quarter is 3 months. Many corporations divide their financial year into quarters, so knowing how to divide data into quarter years is a very useful skill. In this case, it only takes 1 line of code. We'll call the new column quarter, and we'll use our date column with 2_period to create the quarter column. The datetime package has a pre-made code for dividing datetime into quarters. In the 2_period argument field, we only need to place the letter Q. After that, we can use the function strftime to complete the string. For the argument, we put $y dash q $lowercase q. The first Q is placed into the string to indicate we are talking about quarters. The %sign followed by the lowercase q indicates to pandas that we want the date formatted into quarters. Our final column will be the easiest to code of them all. The year column is created by taking our original date column data and creating a string that includes only the argument $y. This creates a column of data with it with only the year in it. Now that we have formatted some strings, let's quickly review our work by using the head function we learned in the previous video. When we run this code, our 4 new columns are there: week, month, quarter, and year. They are all formatted just as we discussed. We can use these new strings to learn more about the data. For example, let's say we want to group the number of lightning strikes by weeks. An organization whose employees primarily work outdoors might be interested in knowing the week-to-week likelihood of dealing with lightning strikes. In order to do that, we'll want to plot a chart. We've reviewed a couple of charts coded in Python by now. Next, let's code a chart with the lightning strike data. For plotting the number of lightning strikes per week, let's use a bar chart. Our graph would be a bit confusing using all 3 years of data. So let's just use the 2018 data and limit our chart to 52 weeks rather than 156 weeks. We can do this by creating a column that groups the data by year and then orders it by week. We will then learn more about these structuring functions in another video. For now, let's focus on plotting this bar chart. We'll use the plt.bar function to plot. Within our argument field, we select the x-axis, which is our week column. Then the y-axis, or height, which we input as number of strikes. Next, we'll fill in some of the details of our chart. Using plt.plot, we will place arguments in the x label, y label, and title functions. The arguments are week number, number of lightning strikes, and number of lightning strikes per week 2018, respectively. This renders a graph, but the x-axis labels are all joined together. So we have a chart, but the x-axis is difficult to read, so let's fix that. We can do that with the plt.xticks function. For the rotation, we can put 45, and for the font size, let's scale it down to 8. After we use plt.show, the x-axis labels are much cleaner. Given our bar chart illustrating lightning strikes per month in 2018, you could conclude that a group planning outdoor activities for weeks 32 to 34 might want a backup plan to move indoors. Of course, this is a broad generalization to make on behalf of every North American location in the dataset. But for our purposes and in general, it is a good understanding of our dataset to have. For our last visualization, let's plot lightning strikes by quarter. For a visualization, it will be far easier to work with numbers in millions, such as 25.2 million, rather than 25,154,365, for example. Let's create a column that divides the total number of strikes by 1 million. We do this by typing df by quarter and entering the relevant column in the arguments field. In this case, we want number of strikes. Next, we add on .div to get our division function. Lastly, for the argument field, we enter 1 million. When we run this cell, we have a column that provides the number of lightning strikes in millions. Next, we'll group the number of strikes by quarter using the group by and reset index functions. This code divides the number of strikes into quarters for all 3 years. Each number is rounded to the first decimal. The letter M represents 1 million. As you'll soon discover, this calculation will help with the visualization. You'll learn more about these functions in another video. We will plot our chart using the same format as before. We use the plt.bar with our x being from our df by quarter data frame with quarter in the argument field. For the height, we put the number of strikes column in the argument field. It would be helpful if each quarter had the total lightning strike count at the top of each bar. To do that, we need to define our own function, which we will call add labels. Let's type add labels, then input our 2 column axes, quarter and number of strikes, separated by columns and brackets. At the end, we use the format we created earlier, number of strikes formatted, to label the number of strikes by quarter. To finish the bar chart, we label the x and y axes and add the title. Before we show the data visualization, there are a few small things we want to add just to make it more friendly to read. Let's set our length and height to 15 by 5. Next, Let's make the bar labels cleaner by defining those numbers and centering the text. Our bar chart now gives us the number of strikes by quarter from 2016 to 2018. To make the information easier to digest, let's do one more visualization. Here is the code for plotting a bar chart that groups the total number of strikes year over year by quarter. Review the code carefully and consider what each function and argument does in order to create this final polished bar chart. Each year is assigned its own color to highlight the differences in quarters. And now we have our chart. Coming up, you'll learn more about the different methods for structuring data. I'll see you there. As a data analytics professional, you will often need to learn more about your data sets. This is where the structuring practice of EDA can help. Let's explore the valuable methods that are part of this practice. As you'll recall from earlier in the program, structuring helps you to organize, gather, separate, group, and filter your data in different ways to learn more about it. Next, we'll talk about the methods involved in structuring, and later you'll practice these concepts using Python. First on the list of structuring methods is sorting. Sorting is the process of arranging data into meaningful order. Imagine that you're given a data set about kangaroos. These furry creatures are native to Australia and Papua New Guinea. They're known for their strong tails and belly pouch they use to cradle their babies called joeys. The kangaroo dataset contains information about kangaroo characteristics like pouch size, tail length, total body length, and much, much more. The first data we'll consider is a data column measuring the volume of the kangaroo pouches in cubic centimeters. We can sort those values in ascending or descending order from biggest to smallest or smallest to biggest. Another useful structuring tool is extraction. Extracting is the process of retrieving data from a dataset or source for further processing. You can think of extraction as retrieving whole columns of data. An example of extraction is to take the kangaroo data from before, then evaluate just two of the columns from the dataset, such as pouch volume and tail length. You can use the resulting data for analysis, comparisons, or visualization. Another structuring method is filtering. Filtering is the process of selecting a smaller part of your dataset based on specified parameters and using it for viewing or analysis. You can think of filtering as selecting rows of a dataset. In the case of our kangaroo dataset, filtering can look like viewing only the kangaroo pouches of kangaroos that also have tails shorter than 1 meter. This is useful in finding meaningful groups or trends in the data. Next on the list of structuring methods is slicing. Slicing breaks information down into smaller parts to facilitate efficient examination and analysis from different viewpoints. Think of slicing as an either or both options for columns and rows, a combination of extraction and filtering. In the kangaroo dataset, let's say you have a column of their body length called total body length. In another column, you have the kangaroos identified as one of the 3 different regional populations. If you were to take the body length of only one of the 3 regional populations, you would be pulling a slice of the data. Grouping is our next structuring method. Grouping, sometimes called bucketizing, is aggregating individual observations of a variable into groups. An example of grouping is to add a new column called total body length next to the kangaroo tail length column. Then, group all the tail lengths into 3 types, long, average, and short, based on the measurements in the tail length column. You can now find and organize the total body length values based on the kangaroo tail length groups. The last structuring method is merging. Merging is a method to combine 2 different data frames along a specified starting column. For example, imagine we had an additional data set of kangaroo information from a different field study, but with the same parameters and variables. We might use the merge or join functions to align the columns and combine the new data into one data set. It's essential that you do not change the meaning of the data while performing your filtering, sorting, slicing, joining, and merging operations. If, for example, we did not merge the kangaroo pouch measurements correctly with their matching kangaroo name and ID, the data would not be representative and our analysis would be far less than useful. Being true to the data is being true to its story. Hopefully, you are beginning to understand the value of organizing and structuring data in order to analyze it. Coming up, we will practice structuring using Python. You've learned about how structuring data can help professionals analyze, understand, and learn more about their data. Now, let's use a Python notebook and discover how it works in practice. We'll continue using our NOAA lightning strike dataset. For this video, we'll consider the data for 2018 and use our structuring tools to learn more about whether lightning strikes are more prevalent on some days than others. Before we do anything else, let's import our Python packages and libraries. These are all packages and libraries you're familiar with: pandas, numpy, seaborn, datetime, and matplotlib.pyplot. For a quick refresher, let's convert our date column to datetime and take a look at our column headers. We do this to get our dates ready for any future string manipulation we may want to do, and to remind us of what is in our data. As you remember, there are 3 columns in the dataset: date, number of strikes, and center point geom, which you'll find after running the head function. Next, let's learn about the shape of our data by using the df_shape function. When we run this cell, we get 3,401,012, 3. Take a moment to picture the shape of this data set. We're talking about only 3 columns wide and nearly 3.5 million cells vertically. That's incredibly long and thin. We'll use a function for finding any duplicates. When we enter df.drop_duplicates with an empty argument field followed by .shape, the notebook will return the number of rows and columns remaining after duplicates are removed. Because this returns the same exact number as our shape function, we know there are no duplicate values. Let's discuss some of those structuring concepts we learned about earlier. Let's start with sorting. We'll sort the number of strikes column in descending value, or most to least. While we do this, let's consider the dates with the highest number of strikes. We'll input df sort_values. Then, in the argument field, type by, then the equal sign. Next, we input the column we want to sort, number of strikes, followed by ascending $false. If we add the head function to the end, the notebook outputs the top 10 cells for us to analyze. We find that the highest number of strikes are in the lower 2000s. That does seem like a lot of lightning strikes in just one day, but given that it happened in August when storms are likely, it is probable these 2,000 plus strikes were counted during a storm. Next, let's look at the number of strikes based on the geographic coordinates, latitude and longitude. We can do this by using the value_counts function. We type in df followed by the center point geom. Then we type in .value_counts with an empty argument field. Based on a result, we learned that the locations with the most strikes have lightning, on average, every 1 in 3 days, with numbers in the low 100s. Meanwhile, some locations are reporting only one lightning strike for the entire year of 2018. We also want to learn if we have an even distribution of values, or whether 108 is a notably high value for lightning strikes in the US. To do this, copy the same value count function, but input a :20 in the brackets so that you can see the first 20 lines. The rest of the coding here is to help present the data clearly. We rename the axis and index to unique values and counts, respectively. Lastly, we'll add a gradient background to the counts column for visual effect. After running the cell, we discover 0 notable drops in lightning strike counts among the top 20 locations. This suggests that there are 0 notably high lightning strike data points and that the data values are evenly distributed. Next, let's use another structuring method, grouping. You'll often find stories hidden among different groups in your data, like the most profitable times of day for a retail store, for instance. For this data set, one useful grouping is categorizing lightning strikes by day of week, which will tell us whether any particular day has fewer or more lightning strikes than others. Let's first create some new data columns. We create a column called week by inputting df.date.dt.isocalendar. Let's leave the argument field blank and add a .week at the end. This will create a column assigning numbers 1 to 52 for each of the days in the year 2018. Let's also add a column that names the weekday. Type in df.date.dt.day_name, leaving the argument field blank. For this last part, let's input df.head again. You'll discover the dates now have week numbers and assigned weekdays. We have some new columns, so let's group the number of strikes by weekday to determine whether any particular day of week has more lightning strikes than others. Let's create a data frame with just the weekday and number of lightning strikes. We'll do this by inputting df double bracket weekday, comma, number of strikes, both in single quotes, followed by more double brackets. Next, we'll add one of our structuring functions, group by, followed by weekday.mean within the argument field. What we're telling the notebook here is to create a data frame with weekday and number of strikes, but then also group the total number of strikes by day of the week, giving us the mean number of strikes for that day. To understand what this data is telling us, let's plot a box plot chart. A box plot is a data visualization that depicts the locality, spread, and skew of groups of values within quartiles. For this dataset and notebook, a box plot visualization will be the most helpful because it will tell us a lot about the distribution of lightning strike values. Most of the lightning strike values will be shown as grouped into colored boxes, which is why this visualization is called a box plot. The rest of the values will string out to either side with a straight line that ends in a T. We will discuss more about box plots in an upcoming video. Now, before we plot, let's set the weekday order to start with Monday. Now, to code that, input G SNS.boxplot. Next, in the argument field, let's have X equal weekday and Y equal number of strikes. For order, let's do weekday order, and for the show flyers field, let's input false. Show flyers refers to outliers that may or may not be included in the box plot. If you input true, outliers are included. If you input false, outliers are left off the box plot chart. Keep in mind, we aren't deleting any outliers from the data set when we create this chart. We're only excluding them from our visualization to get a good sense of the distribution of strikes across the days of the week. Lastly, we will plug in our visualization title, Lightning Distribution per Weekday for 2018, and click Run Cell. Now you'll discover something really interesting. The median, indicated by these horizontal black lines, remains the same on all of the days of the week. As for Saturday and Sunday, however, the distributions are both lower than the rest of the week. Let's consider why that is. What do you think is more likely? That lightning strikes across the United States take a break on the weekends? Or that people do not report as many lightning strikes on weekends? While we don't know for sure, we have clear data suggesting the total quantity of weekend lightning strikes is lower than weekdays. We've also learned a story about our data set that we didn't know before we tried grouping it in this way. Let's get back into our notebook and learn some more about our lightning data. One common structuring method we learned about in another video was merging, which you'll remember means combining two different data sources into one. We'll need to know how to perform this method in Python if we want to learn more about our data across multiple years. Let's add 2 more years to our data, 2016 and 2017. To merge 3 years of data together, we need to make sure each data set is formatted the same. The new data sets do not have the extra columns week and weekday that we created earlier. So, to merge them successfully, we need to either remove the new columns or add them to the new data sets. There's an easy way to merge the 3 years of data and remove the extra columns at the same time. Let's call our new data frame union_df. We'll use the pandas function concat to merge, or more accurately, concatenate the 3 years of data. Inside the concat argument field, we'll type in df.drop to pull the weekday and week columns out. We also input the axis we want to concatenate, which is 1. Lastly, and most essentially, we add the data frame name we are concatenating to, df_2. We also input true for ignore index because the 2 data frames will already align along their first columns. And now, you've just learned to merge 3 years of data. To help us with the next part of structuring, create 3 date columns following the same steps you used previously. We've already added the columns for year, month, and month_text to the code. Now, let's add all the lightning strikes together by year so we can compare them. We can do this by simply taking the 2 columns we want to look at, year and number of strikes, and group them by year with the function .sum on the end. You'll find that 2017 did have fewer total strikes than 2016 and 2018. Because the totals are different, it might be interesting as part of our analysis to see lightning strike percentages by month of each year. So let's call this lightning by month, grouping our union data frame by month, text, and year. Additionally, let's aggregate the number of strikes column by using the pandas function named ag. In the argument field, we place our column name and our aggregate function equal to sum so that we get the totals for each of the months in all 3 years. When we input the head function, we have the months in alphabetical order along with the sums of each month. We can do the same aggregation for year and year strikes to review those same numbers we saw before, with 2017 having fewer strikes than the 2 other years. We created those two data frames, lightning by month and lightning by year, in order to derive our percentages of lightning strikes by month and year. We can get those percentages by typing lightning by month dot merge with lightning by year, comma, on equal sign year in the argument field. You'll find that the merge function is merging lightning by year into our lightning by month data frame according to the year. Lastly, we can create a percentage lightning per month column by dividing the percentage lightning dot number of strikes by percentage lightning, after which we'll add the asterisk 100 to give us percentage. Now, when we use our head function, we have a restructured data frame. To more easily review our percentages by month, let's plot a data visualization. For this one, a simple grouped bar graph will work well. We'll adjust our figure size to 10 and 6 first. Then we use the Seaborn Library bar plot with our x-axis as month text and our y-axis as percentage lightning per month. For some color, we'll have our hue change according to the year column with the data following the month order column. Finally, let's input our X and Y labels and our title and run the cell. When you analyze the bar chart, August 2018 really stands out. In fact, more than 1/3 of the lightning strikes for 2018 occurred in August of that year. The next step for a data professional trying to understand these findings might be to research storm and hurricane data to learn whether those factors contributed to a greater number of lightning strikes for this particular month. Now that you've learned some of the Python code for the EDA practice of structuring, you'll have time to try them out yourself. Good luck finding those stories about your data. You know that moment in the puzzle building process when you're starting to see the full picture take shape? Like maybe you have the frame pieces connected, but still have a way to go? So far, you've learned about some practices of EDA. You've learned how to gather, analyze, organize, and structure data. Coming up, you will continue to put these pieces together and the picture will become clear. You're making great progress. You've learned about the data sources, data types, and data formats, and the importance of knowing the basics about your data. We've worked through how to use Python to uncover big picture understandings of your data sets, like column headers, d-types, size, and shapes, as well as basic visualizations. Along with these parts of EDA and discovering, we've learned about date and time transformations in Python. As for the EDA practice of structuring, you've learned to make order from chaos with functions like sorting, extracting, filtering, slicing, joining, merging, and grouping. In Python, you practice applying these functions to datasets that are similar to those you might work with in your career as a data professional. Data professionals commonly use each of these concepts. You will continue to build your skills with them as you search for the stories hidden in data. As a data professional, I can say that cleaning and organizing your dataset is 90% of the battle. And once you've structured your tables, uncovering insights and trends can be like a walk in the park. I mentioned earlier how I used to work as a data analyst in healthcare consulting and would analyze vast amounts of medical record data to help recommend treatments for patients with severe illnesses. Typically, data is hosted across multiple different sources and tables, making them difficult to merge together. Plus, medical records may be organized so that medications a patient took and their corresponding conditions are separated. So, in order for me to understand what type of treatment a patient took for which illness, the side effects they experienced, and whether the treatment worked, I had to merge hundreds of tables together. Once I did, it was incredibly easy for me to compare and contrast the different types of treatments taken and its impact on each patient. You started to learn the skills needed to complete similar tasks. Along the way, You also learned some key workplace skills like the timing for communicating updates and posing questions to project stakeholders, managers, and subject matter experts. We also talked about making and testing hypotheses on your datasets, which narrows the scopes and sharpens the detail of your data-driven stories. In short, you are understanding more and more what it means to perform EDA on a dataset. Great work. Later in the program, we'll discuss how to put together the rest of the data story by learning what to do with missing data and outliers, as well as making and using visualizations to help tell that story. I'll meet you there. Let's imagine you work at a board game manufacturer. As the quality assurance manager, your job is to make sure every game is put together correctly. One day, you discover that the machine that produces the games is having technical issues, causing misprinted cards and incorrect counts of game pieces. Your manager asks you and the rest of the quality assurance team to go through the affected boxes and replace misprinted cards and missing pieces. Your goal is to make sure each box is usable. Searching through game boxes for missing and incorrect game pieces is similar to cleaning, joining, and validating your datasets as part of exploratory data analysis, or EDA. Earlier, you learned how to discover and structure data in order to understand and tell its stories in impactful ways. In this part of the course, we will cover 3 of the other practices of EDA: cleaning, joining, and validating data. Although there are many different ways to clean, join, and validate data, we will focus on missing values and outliers, the need for transforming categorical into numerical data, and the importance of input validation. Of course, we won't just talk about the concepts of cleaning, joining, and validating. You will learn how to apply them in a Python notebook setting. We'll use datasets that are comparable to what you will see on the job. Along the way, we'll go through some important tips for improving your workplace skills like communication. We will discuss when to communicate with stakeholders and engineers about missing or outlier values and about the ethical implications you must consider when dealing with missing and outlier data values. These practices of EDA, along with effective communication and Python coding, are all essential to preparing a dataset for the next steps in the PACE workflow. By following PACE while performing the 6 practices of EDA, you will not only save time and energy on future processes, but you will be more effective in finding and telling the data story. One of my first jobs at Google was a quantitative analyst on Google Translate. It was my responsibility to help identify areas that we could improve to help users. I recall a project where I was overly eager to dive into the data. I spent countless hours identifying opportunities ranging from when a user first downloads the app to their 2nd, 3rd, and 20th time using the product. I was proud of my findings, and I developed a long presentation to share with my executives. Now, while my insights were well received, the team was reluctant to invest in any of my ideas because there were so many, and they weren't sure which ones to prioritize. I realized after that meeting that I needed a plan. I'd spent so much time mining for insights that I was suffering from what my manager called analysis paralysis. Instead, what I needed to do was find out what issues were affecting the most number of users and the severity of it. By organizing my thoughts using this strategy, I was then able to hone my analysis into one specific issue and then recommend clear actions to help. Like your job as a quality assurance manager that we imagined at the beginning of this video, as a data professional, you may be responsible for cleaning up data sets so that they are ready to use. You won't always be sure what obstacles you may face with cleaning data, so let's get started on some of the most common. Remember earlier when you imagined yourself as a quality assurance manager at a company assembling a board game? When you discovered that the machine that produces the games was having technical issues and causing game boxes to have pieces missing, you and your company could have chosen a different number of paths forward. 1, you could have thrown away the impacted game boxes. 2, you could have left them as is and sold them at a discounted rate. Or 3, and the one you chose in the example, you rummaged through the boxes and corrected the mistakes. There was a plan, strategy, or protocol for dealing with missing pieces. The same should be true for any missing values you find in a data set. When you have missing entries in your data set, you have to decide on a plan for dealing with them. Even more than that, you must be ready to communicate with stakeholders if missing values impact your analysis. Missing data, which is often encoded as a NA, NaN, or blank, is defined as a value that is not stored for a variable in a set of data. This is different from a data point of 0. I'll explain more on that in a bit. Data professionals often experience the challenge of missing data. Every data set is different, so there are a wide variety of reasons for values to be missing. Everything from a computer error during a data upload to someone simply forgetting to input it. Depending on the number of entries in your dataset and the quantity of missing values, the impact of data fields with a not a number or NaNs can range from negligible to substantial. The impact will also determine how you communicate to stakeholders or clients, ranging from a note at the bottom of a data visualization about the fact that there's missing data, to a face-to-face meeting about how analyses cannot be completed due to the large number of missing values. Here's an example of the impact missing data has on a dataset and the ethical questions missing data creates. Imagine you're a data professional trying to learn more about sleep habits. You email a questionnaire to, say, 100 people, and all of them complete it. One of the questions asks, do you sleep exactly 8 hours each night? The answer choices are yes, no, or unsure. 9 people answer yes, 9 answer no, and 15 answer unsure. Because only 33 people responded to that question, it's hard to draw a definitive conclusion about the sleep habits of all 100 students. Since 100 people completed the questionnaire and only 33 responded to this question, 67% of the replies would be considered missing. These missing values greatly impact the question's resulting data. It would be unwise for a data professional to try to use the 33% response rate in order to draw conclusions about the entire population. If you encountered this level of missing values while working as a data professional, you should communicate the inability to complete any analysis and suggest possible solutions. Another challenge that can come up during EDA is with the value 0. In some datasets, a 0 could be considered a missing value, but in other datasets could be a legitimate data point. In some datasets, a NaN or blank space might be a mistake. Someone forgot to fill it in. Or the data may have been left blank because the column may not apply to that data point. Data professionals unsure of whether or not the blank space is intentional should ask a stakeholder or the owner of the data to confirm the space's legitimacy. Whenever you find missing data, you have a choice to make on how to handle it. As a data professional, you should consider how the missing data might impact stakeholders and who should be made aware. Here are 4 common ways to handle missing data. 1. You requested the missing values be filled in by the owner of the data. 2. You delete the missing columns, rows, or values, which would work best if the total count of missing data is relatively low. 3. You create a NaN category. Or 4. You derive new representative values, such as taking the median or average of the values that aren't missing. First, we'll talk about filling in the missing data. If there are large quantities of missing values in the data you receive, the best method to handle the missing data would be to contact the owners of the data and request that that data be filled in. For example, in our sleep example, you could send a follow-up request for people to log a response to that particular question. Or you could rephrase the question, how many hours do you sleep each night? However, in many data sets, you'd see while working as a data professional, the option to get missing data filled in may not be feasible for a variety of reasons. For example, if you're working on a project that is time sensitive, you might not have time to gather more data before your deadline. Or the data cannot be retrieved because the study happened too long ago. If filling in missing data isn't an option, you can also choose the option of deleting the missing data. Though some might assume it's not appropriate to delete data, removing rows or whole columns of data is ideal if there isn't a large percentage of nans, or the values are not going to impact the business plan for the data. One thing to watch out for, though, is discarding missing data that is not missing at random. Deleting values that have been left blank intentionally can skew the results of your analysis. For example, in the sleep questionnaire, if you were to remove all the people that left that question blank, you delete a majority of the data. A third option is to make the nans their own category, which is a good strategy if the missing data itself is categorical rather than numerical. For example, in the sleep questionnaire, if you were to put all the non-responses into their own category called answer not recorded, you would be creating a category for the missing data. Finally, there's the strategy of filling in the missing data by creating a representative value. This strategy can be more useful with business plans that call for a predicted value or forecast. There are multiple methods within this filling in strategy to choose from, including the four most common: forward filling, backward filling, deriving mean values, and deriving median values. We will talk about how to do all these missing data operations using Python in another video. These are the most common methods for handling missing data. Choosing which method to use comes with experience, intuition, and reasoning. Sometimes you'll have the opportunity to use more than one option with a dataset. Every dataset and project plan will be different, so you will be making this determination each time you encounter new data. Sometimes you'll want to confer with peers or managers or stakeholders in order to make a decision. The impact missing values has on your analysis should be the determining factor in whom you should contact. As a data professional, it is essential that you are thoughtful and intentional about how missing data are addressed. Consider the quantity of nans and their importance in relation to the project plan. Ask yourself, how will this approach impact this data set? And what are the ethical considerations? Just like the board game scenario, it is essential to determine a strategy and decide on a plan. Now that we reviewed the importance of having a plan to address missing data, let's talk about how to identify and decide how to work with missing data in a Python notebook. We'll use the data you're familiar with, the group of NOAA lightning strike datasets. The goal of this video is to learn how to identify missing data. You'll be provided two different slices of data from August 2018. One slice will have the columns date, center point geom, latitude, longitude, and number of strikes. The second slice of the data will include the same columns as the first slice, along with the zip code, state, city, and state code. You will learn through comparisons of these two data sets how to find missing data. Before we look for any missing values, we need to import some Python libraries and packages. We'll use pandas, numpy, seaborn, datetime, and pyplot from matplotlib. We will begin by looking at only the number of lightning strikes for August 2018. Using less data in a Python notebook allows you to spend more time coding and less time waiting for the code to run. For this exercise, our first data set will have two additional columns called latitude and longitude, which were points pulled from the center point geom column. Let's explore the column headers and the overall size of this first data set using the functions that you're already familiar with, head and shape. We'll find the two additional columns we just mentioned for latitude and longitude as well as a shape of 717,530 rows and 5 columns. Let's put this aside as our first data frame, saved as DF. Next, we'll use the second data set for August 2018. This one has columns for zip code, which is a postcode delivery area number in the US, as well as city, state, and a column titled state code that has 2-letter abbreviation of states in the US. We'll call this second data frame dfzip so we don't get confused with the first data set we created earlier. Let's run the same two functions, head and shape, on dfzip. The head function returns what we expected out of the top 5 columns of the data set. The data columns zip code, city, state, state code, center point geom, and number of strikes. The shape function, however, returned 323,700 rows and 7 columns. Given that this data frame is also from August 2018, we expected to see the same number of rows as the first data frame, 717,530. To further explore this, let's put the two data frames together with the merge function. We'll need to create a new data frame. We'll call it dfjoined, followed by an equal sign and df.merge. This df.merge indicates that we want to merge the first data frame we saved, named df, with another data frame. For the merge, put df_zip in the argument field, which is the data frame we want to merge with df. Next, fill in the parameters for the merge, including how equals left followed by a comma. Finally, input the last parameter, on equal sign followed by 2 column names, date, and center point geom. These 2 parameters, how and on, tell Python which way to join the data from left to right and which column to start from, date and center point geom, respectively. When we run the head function on our new data frame, we find nans listed for the columns zip code, city, state, state code, and number of strikes y. Now that the data is merged, let's use a basic function we learned in a previous lesson to search for missing data, describe. Input df_joined.describe and leave the argument field blank. When we run the cell, we find that the total count of lightning strikes has been divided into 2, number of strikes x and number of strikes y. Once we merged the 2 data frames, Pandas automatically separated number of strikes into data entries with full data rows and data entries that have missing entries. We can find the total amount of data that's missing using this next piece of code. We'll create a data frame called dfnullGeo by taking our join data frame, dfjoined, and then adding the pandas function isNull, all one word. The term null indicates that the data is missing. This function pulls all of the missing values from the dfjoin data frame. We already know which of the columns have missing values. Since we're interested in finding the total, we can use any one of those columns. For this code, we selected state code. After that, we'll use the shape function to give us the total rows and columns, which comes to 393,830 and 10, respectively. For even more detail, use the info function, which we used in another video. When we input dfjoined.info with the argument field left blank, we get the column names and another column called non-null count. Non-null count is the total number of data entries for a data column that are not blank. A quick check of the non-null count column helps us confirm which columns have missing data: zip code, city, state, and state code. In fact, If we subtract the total number of strikes x and the number of strikes y, the result is the number we identified earlier, 393,830. Let's take a look at the top portion of the new data frame we created, df null geo, using the head function. The output tells us exactly what we expected to find in the data frame we created. In the top 5 lines of data, the columns zip code, city, state, state code, and number of strikes y have the nan values in the cells. Now that we've pinpointed exactly what values are missing in our data frame, the last thing we'll do in this notebook is learn how these missing values impact our data. The best way to do that is to create a data visualization. A plotted map will help us see where the majority of the missing values are located geographically. To design the map, let's start by creating another data frame. This one we'll call top_missing. With this data frame, we are gathering only the data columns we will need in order to plot a geographic visualization: latitude, longitude, and number of strikes x. As you'll recall from earlier in this video, number of strikes x includes all of the 717,530 data rows, while number of strikes y are a segment of those 717,530 with missing data in the zip code, state, and state code columns. You'll find that it's helpful to group the columns by latitude first, then longitude. This will make it easier for most data processors to plot. Lastly, we'll sort the lightning strikes x column by sum of values. In the ascending field, we'll input false because we want the largest sums of lightning strikes at the top of the data frame. Finally, let's take a look at what we built using the head function again. After running the cell, the first 10 rows show the most strikes are falling on and around the same latitudes and longitudes. Let me give you a helpful hint before we plot a visualization using this data frame. You should import the Express package from Plotly first. Express is a helpful package that speeds up coding by doing a lot of the back-end work for you. If we don't use Express for this particular dataset, which has hundreds of thousands of points to plot, your run cell times could be long, or the code could even break. Now it's time to create the map. Our format for the graph will be from Plotly Express called scatter geo. As indicated by its name, this graph type is used for scatter plots on a geographic map. In the argument field, we'll input the data frame we just created, top missing. For the parameters in the argument field, we want to filter the number of values to be only those latitudes and longitudes with lightning strikes of more than 300. Naturally, we plug latitude and longitude into their appropriate parameter spots. Then, for the size parameter, we plug in the final column, number of strikes x. Lastly, let's use the update layout function within the figure to give the plot title, missing data. Now we create it. It's a nice geographic visualization, but we really don't need the global scale. Let's scale it down to only the geographic area that we are interested in, the United States. So let's copy the same code we just wrote. This time though, we add the parameter geo_scope equals USA. This will limit the geographic scope to just the United States of America. Then we can plot it again and check the output. The resulting map shows a majority of these missing values cropping up along the borders or in spots over bodies of water, like lakes, the ocean, or the Gulf of Mexico. Given that the missing data were in the state abbreviations and zip code columns, it does make sense why those data points were left blank. There are no zip codes for bodies of water. You'll also notice some other locations with missing data that are not over bodies of water. These types of missing data, latitude and longitude on land, are the kind of missing data you would want to reach out to the NOAA about. What's interesting about cleaning the lightning strike data and looking for missing data values is that we learned something new in the process. We found one of the stories hidden in the data. The data values were missing because the lightning strikes were over water. It goes to show you that data cleaning may sound tedious, but you'll never know what you learn. As a child, did you ever play a puzzle game in which you were supposed to look at a picture and find an object that doesn't belong? Maybe sometimes the object was obvious, but other times it may have been more difficult. For example, if you were given a picture of a bustling marketplace full of people selling fruits, vegetables, and grains, it would probably take some time to find the item for sale that's not in the right place. Similar to visiting a busy market, when you encounter a data set that hasn't been cleaned, it can be really challenging. Data may at first seem structured, but it often can be hard to determine whether there are any data points that are measurably different from others. These extreme data observations, the ones that stand out from others, are known as outliers. Outliers are observations that are an abnormal distance from other values or an overall pattern in a data population. In this video, we will discuss the three main types of outliers and why it is important for data professionals to identify them in the data we analyze. As a data professional, you should be fully aware of the beginnings and ends, highs and lows, and extreme points of your data across every variable in the data set. These values will often be your outliers. It is essential that you recognize them, what their value is, and where they are. Otherwise, they will likely skew any conclusions you draw or models you build from it. There are three different types of outliers we will discuss in this video: global, contextual, and collective outliers. Later, you'll learn how to find outliers and work with them in Python. The first outliers we'll discuss tend to be the easiest data points to detect. Global outliers are values that are completely different from the overall data group and have no association with any other outliers. They may be inaccuracies, typographical errors, or just extreme values you typically don't see in a data set. For example, if we had a set of human heights, 1.7 meters, 1.9 meters, 1.6 meters, 1.8 meters, 7.9 meters, 1.8 meters, or 1.7 meters, the outlier is fairly obvious. Typically, global outliers should be thrown out to create a predictive model. Contextual outliers can be trickier to spot. Contextual outliers are normal data points under certain conditions but become anomalies under most other conditions. As an example, movie sales are expected to be much larger when a film is first released. If there is a huge spike in sales a decade later, that would typically be considered abnormal, or a contextual outlier. These outliers are more common in time series data. Another example might be an outlier only in a specific single category of data. For instance, 2.5 meters may be a normal enough size for a category called mammal heights, but if the mammal is found out to be a mouse, we would likely consider this an outlier, despite it fitting in with other mammal heights. Lastly, we have collective outliers. Collective outliers are a group of abnormal points that follow similar patterns and are isolated from the rest of the population. Think of a parking lot at a store. It is not uncommon to have cars or scooters coming and leaving consistently during the hours a store is open. But to have a full parking lot after the store is closed would be considered a collective outlier. It could be that there is a company party or a local event nearby, which would explain the outlier of cars parked in the store parking lot after hours. One useful way to find these different types of outliers in our data is something we've already discussed quite a bit: visualization. It will be easier to see any big dips or giant blips in the data when we plot it on a line graph or a bar chart. No matter how you discover that your data contains global, contextual, or collective outliers, it is essential that your EDA includes a strategy for dealing with them. It will be up to you to decide how outliers need to be represented or whether they need to be removed completely. The decision on what to do must always be done in the context to the dataset and the business plan for the data. As mentioned in other videos, always consider the ethical implications of any decision you make about outliers. When you're working as a data professional, it may be tempting to remove outliers to improve results, predictions, or forecasts, but you will need to ask yourself, does that change the data story? For example, let's imagine that you are a data professional at a retail business. You review 2 years of sales data and find that there's 1 month where sales of a typically popular item are down dramatically. You might at first assume that there's a typo in the reported data, but as a diligent data professional, you ask questions about it. You discover that several top salespeople were on leave during that month, and your company advertised a new product which slowed sales on the existing item. It is likely that both of these issues led to a drop in sales. Rather than dismissing the drop in sales as an outlier, this information will be helpful for the business team. Using this information, managers can prevent a future drop in sales numbers ahead of the product launches by hiring additional sales team members or limiting requested employee leave during those critical times. Later, you'll learn how to find outliers and work with them in Python. Earlier, you learned about 3 types of outliers: global, contextual, and collective. Now that we discussed outliers on a conceptual level, I'll show you how to identify them and analyze their impact in a Python notebook. Our goal will be to identify outliers across a 33-year span of total lightning strike counts in the United States. As usual, let's start by importing our libraries and packages: pandas, numpy, seaborn, and pyplot from matplotlib. We'll continue using our NOAA lightning strike dataset. This time, we'll group the total sum of the lightning strikes in the United States by year from 1987 to 2020. Let's first reveal the top 10 rows of data using the head function. The dataset has 2 numeric columns: year and number of strikes. As you'll notice, we're dealing with some fairly large numbers for the lightning strike totals. It would be helpful to make them a bit shorter and easier to read in visualizations. To do that, let's write a readable numbers function. Below the function, there is a long explanatory text inside a triple set of quotation marks. This is called a documentation string, or docstring. A documentation string, or docstring, is a line of text following a method or function that is used to explain to others using your code what this method or function does. A docstring represents good documentation practice in Python. It makes the code easier to understand and can be easily exported to create library documentation. A docstring was already provided for this readable numbers function. Next, we'll form an if-else statement. We want to code any number above 6 digits to be formatted to 1 decimal place, followed by an M. Under the else statement, we are formatting numbers with more than 3 digits to the same 1 decimal place, followed by the letter K. Under these statements, we define the new data frame we want, titled number of strikes readable. We then use the apply function to set our readable numbers statement to only the number of strikes column in the data frame. Using the head function, we'll see the output of our newest code. The new column has readable values of 15.6 million, 209,000, and 44.6 million in its first 3 rows, where before there were just long strings of numeric digits. This indicates that we coded the read numbers function correctly. Now that we have more readable values, let's plot our data. As you'll recall, our goal is to find any outliers among the total number of lightning strikes in 33 years of NOAA data. One way to find any outliers would be to investigate the mean and median of this data. The mean is the average number of the given values, and the median is the middle point of the given values. When we code for these two values, we use the NumPy functions of mean and median. We're using the readable numbers for simplicity. The resulting output is the mean, 26.8 million, and the median, 28.3 million. With the mean being 2 million strikes less than the median, we suspect the data distribution is likely skewed to the left. The left side of the distribution will be a good place to investigate. One effective way to visualize outliers is a box plot. As we discussed in a previous video, a box plot divides the distribution of data points into 4 main quadrants or quartiles. The box plot is helpful in visualizing and confirming the outliers we've already found. Let's plot the box plot first, and then we'll talk about it in more detail. To design a box plot using Python, we'll use the Seaborn box plot function. We'll use the number of strikes column from our data frame as the basis for the plot. Next, we'll use setXTick labels based on the readable numbers statement we created already. XTick labels simply allow us to give names to the x-axis marks so that they are read more easily. Lastly, we input the x and y labels and the title. You'll recall that the purpose of a box plot is to show the distribution of values separated into quadrants or quartiles. What we are most focused on with our plot are that the 2 points beyond the far left of the line are below 10 million. This data visualization is showing us very clearly there are outliers included in our group of data points. The blue rectangles in your box plot are called the interquartile range. This range represents the difference between the third quartile and the first quartile of a set of data values. A standard rule of statistics, which you'll learn more about in another course, is that any data point that falls beyond 1.5 times the blue boxes are considered outliers. This next piece of code will help us define what value is at 1.5 times below our interquartile range. We'll use the quantile function to define what we'll call percentile 25 and percentile 75. We enter our data column, number of strikes for our data frame, and then 0.25 and 0.75 in the argument fields. The values that occur between the 75th and 25th percentile are the interquartile range. We create a statement for interquartile range, IQR, defining percentile 75 minus percentile 25 is equal to IQR. Now, let's define two statements, upper limit and lower limit. Upper limit is equal to percentile 75 plus 1.5 times IQR. Lower limit is percentile 25 minus 1.5 times the IQR. Lastly, let's have Python provide the exact value of the lower limit. We'll input print followed by the text lower limit is colon plus sign readable numbers and lower limit in the argument field. After running the cell, we learn that the lower limit is 8.6 million. Don't worry if you're still trying to understand interquartile range. This concept will be explored further in depth later in the program. Next, let's plot the values that lie below our lower limit of 8.6 million. Place the number of strikes column inside the brackets next to DF. Then, use the less than symbol followed by the lower limit we just derived. And now, here are the outliers. One great way of seeing these outliers in relation to the rest of the data points is a data visualization. For this plot, let's do a scatter plot. You may recall that a scatter plot represents relationships between different variables with individual data points without a connecting line. To start the scatter plot, let's first add labels to each point on the plot. We'll define them using the add labels function for x and y points. The plt.text function allows us to define how we want the text of each data point to appear. In this case, we tell the text to start 0.5 pixels to the left of the data point and to start 0.5 pixels above the data point. We also define the number of values using our readable numbers statement from the beginning of the video. Next, let's add color to the data points. Let's make the outlier points red and the other points blue. To do that, we'll define colors by the lower limit. For those that fall below our previously defined lower limit, we'll code that they should be R for red, and everything else will code as B for blue. Our next line of code should feel familiar. We start by configuring our visualization size. In this case, we code 16 and 8 inches, which are the default units for this function. Next is our code for scatter plots, ax.scatter. The ax refers to axis, which tells the notebook to plot the data on an x versus y data graphic. Inside the argument field, we first input the x-axis and then the y-axis, which is year and number of strikes, respectively. For the rest of the parameters, we fill in the x and y label and the title. We finish the parameters of our scatter plot by defining the x-axis tick labels and setting the rotation of the x-axis ticks to a rotation of 45 degrees. The resulting plot shows us the years 1987 and 2019 are the two values in red, our two outliers. Now that we've narrowed our scope of the outliers to just 2 years, 1987 and 2019, we can do a little more investigating. Let's start with the 2019 lightning strike data. If we import just the 2019 data, the first thing we'll want to do, as we learned in a previous video, is convert our date column to date time. Next, we'll create some new columns in our data frame, month and month text. You'll notice for the date, we use the str.slice function to cut the month names down to just the first 3 letters. Finally, we create a data frame that groups the total number of lightning strikes for each month. The result explains why the year is an outlier. For the 2019 dataset, only lightning strikes from the month of December have been inputted. If you were a data professional tasked with calculating lightning strike risk, you would first research the NOAA documentation available to see if there's a reason given. If you don't find anything based on your research, you would then ask the NOAA why lightning strikes haven't been recorded for the other 11 months of 2019. When we do the same code for 1987, the resulting output is different from 2019. We find there are lightning strikes recorded for each month in 1987. This difference, that 2019 does not have data for all months and that 1987 does have data for all months, helps us to know how to handle these two outliers. For 2019, it would make sense to exclude it from our analysis. As for 1987, we recognize that it is indeed an outlier, but it should not be excluded from our analysis because it does have lightning strike totals included for each month of the year. Now, before we end, let's return to the mean and median values that we calculated earlier. First, let's create a new data frame including only data points that exclude the outliers we identified. Our goal here is to show the mean and median of the dataset excluding the outliers. To do this, we'll use a data frame without outliers we just created and our readable numbers statement to only include data points that are greater than our lower limit. When we exclude those outliers, the mean and median are much closer together, suggesting a fairly evenly distributed data set. Now, let's revisit the goal we set earlier: to identify outliers across the 33-year span of total lightning strike counts in the United States. We discussed a lot of new concepts, and we achieved this goal. Have you ever tried to charge your phone with the wrong type of plug? It is a frustrating problem, but definitely not an insurmountable one. You will probably experience a similar frustration when you work with categorical data. Categorical data is data that is divided into a limited number of qualitative groups. For example, demographic information tends to be categorical, like occupation, ethnicity, and educational attainment. Another way to think about categorical data is data that uses words or qualities rather than numbers. As a data professional, you will likely work with data sets that contain categorical data. Categorical data entries can typically be identified quickly because they are often represented in words and have a limited number of possible values. Many data models and algorithms don't work as well with categorical data as they do with numerical data. Assigning numerical representative values to categorical data is often the quickest and most effective way to learn about the distribution of categorical values in a data set. There are some algorithms that work well with categorical variables in word form, like decision trees, which you'll learn about in another course. However, with many data sets, the categorical data will need to be turned into numerical data. This conversion is often essential for predicting, classifying, forecasting, and more. There are several ways to change categorical data to numerical. In this video, we will focus on two common methods: creating dummy variables and label encoding. One way to work with categorical data is to create dummy variables to represent those categories. Dummy variables are variables with values of 0 or 1, which indicate the presence or absence of something. It helps to open a dataset with dummy variables already created to understand what their function is. You'll find in this dataset that for any value that has been determined to be mild, A1, has been input. All other values in the mild column are labeled with zeros. The same goes for other categories and values. You can think of it as the 1 representing a yes and the zeros representing a no. Dummy variables are especially useful in statistical models and machine learning algorithms. Another way to work with categorical data is called label encoding. Label encoding is a data transformation technique where each category is assigned a unique number instead of a qualitative value. For instance, let's imagine you had a dataset about mushrooms in which you wanted to understand the distribution among different types of mushrooms. Imagine you've been given a dataset about mushrooms with a column titled type and the options of black truffle, cremini, king trumpet, button, hedgehog, morel, portobello, toadstool, or shiitake. You could use label encoding to transform each mushroom type into a number. Black truffle would be changed to a 0, button would become a 1, cremini a 2, hedgehog a 3, king trumpet a 4, morel 5, portobello 6, shiitake 7, and lastly, toadstool would be 8. So why do data professionals use label encoding? Data is much simpler to clean, join, and group when it is all numbers. It also takes up less storage space. An algorithm or model typically runs smoother when we take the time to transform our categorical data into numerical data. For example, let's say you try to run a prediction model using the mushroom dataset, which will try to anticipate the percent chance a new mushroom introduced to the data is a portobello. If we try to create a model without first performing the label encoding, the prediction model will not function. Of course, there will be models and algorithms in which you may not want to perform label encoding. Let the business need be your guide on whether or not you'll need to perform label encoding. The type of model or algorithm you choose will determine whether or not you encode labels. You'll learn more about algorithms and models in an upcoming course. Much like making sure you have the right phone charger to plug into your phone, as a data professional, you need to make sure your data is ready to use with models or algorithms. In a previous video, you learned about the importance of label encoding, also known as transforming categorical data into numerical data. Now it's time to open our Python notebooks and learn how to do it. Let's continue with the same NOAA dataset we've been using for lightning strike counts. For this notebook, we'll look at data from 2016, 2017, and 2018. Let's start by importing Python libraries and packages. For this notebook, let's import datetime, pandas, seaborn, and pyplot from matplotlib. As you learned previously, start by converting the date column into datetime, which makes it easier to manipulate. Next, create a column called month. Like we did earlier, we will use str.slice to cut the month names down to only the first 3 letters. When working with this data, it is helpful to make sure the month names stay in chronological order. Our next line of code then is months, which simply defines the group of months in order. You'll find this helpful in the next line of code, where we use the pandas function, categorical, to group the number of strikes column by the month column. Because we have 3 years worth of data, let's also create a column listing the year. To do this, we name the column year using the datetime function strftime. This function will return a string representing only the year in the original date column. Inside the argument field, we input $y, indicating we only want the year from the datetime string. Finally, let's create a data frame called df by month, which groups the number of strikes first by year and then month. The last part of the code here is making sure that the number of strikes is added together for each month using the sum method. We'll tack on the reset index function to tell the notebook to recount the rows from 0 without using its initial order. When we look at the top of the data frame using the head function, we get the first 5 rows of data with columns of year, month, and number of strikes. Let's create a column for categorical variables called strike level. In this column, we will group or bucket the total number of strikes into categories: mild, scattered, heavy, and severe. This is how we perform label encoding in Python. To do this, we'll create a new column in our df by month data frame called strike level. This new column will be coded using the pandas function, qcut. The q in this function refers to quantile, meaning that when using this pandas function, you can cut the data into 4 equal quantiles. For its parameters, we first input the desired column we want to cut into quantiles, which will be the column called number of strikes. Then we input the number of quantiles we want, which is 4, 1 for each classification. We type in those classifications under the label parameter mild, scattered, heavy, and severe. Let's use the head function to find out how our code modified the data frame df by month. It may seem counterintuitive to create categorical data in order to then transform it to numerical data, but this process will allow us to segment the data into useful chunks, which can then be plotted on a graph in interesting ways. Not to mention, string categories are easier to understand in a data visualization than numbers. One other column which will help us later is to assign numerical values to the strike levels we just defined as mild, scattered, heavy, and severe. We'll call this new column strike level code. We'll define it by taking the column strike level and adding .cat.codes. Cat codes is a pandas function that takes categories and assigns them a numeric code. In this case, when we run the cell, we find that mild has been assigned a 0, scattered assigned a 1, heavy a 2, and severe a 3. And that's how we perform label encoding. Having both the categorical terms for different levels of lightning strikes and the numeric codes to go with them, we can create data visualizations or models that are straightforward to interpret. One other helpful way to work with categorical data is to create dummy variables to represent those categories. As you'll recall from a previous video, dummy variables are variables with values of 0 or 1, which indicate the presence or absence of something. The pandas function we'll use to achieve this in our Python notebooks is called getDummies. To clarify, new columns of ones and zeros are also known as dummies. The get_dummies function converts these categorical variables, mild, scattered, heavy, and severe, into numerical or dummy variables from the column called strike level. If we run the cell, you'll find this function creates 4 new columns and puts a 1 in any row where the number of lightning strikes falls into the labeled category, and a 0 for anything else. Now that we have our new columns of categorical data, numeric data, and dummy variables, let's discover what you could potentially learn from these groupings. To do that, let's plot our data. We'll first create a data frame called df by month plot. Let's reshape the data by using the pandas function, pivot. Pivot allows us to reshape our data frame into any given index or set of values we want based on the parameters inside the pivot function. Those parameters are index, columns, and values in that order. To help us with the visualization, let's use year in the index field, month in the columns field, and strike level code in the values field. If we use our head function, we find all 3 years in the rows, the months in the columns, and the strike level categories in each month, just like we coded. Next, let's visualize our data using what is called a heat map, so we have a better idea of where most of the lightning strike values are. A heat map is a type of data visualization that depicts the magnitude of an instance or set of values based on 2 colors. It is a very valuable chart for showing the concentration of values between 2 different points. Let's create a heat map using Python. Using the heat map plot from Seaborn, we can place df by month plot in the parameter field for the data along with cmap equals blues. This cmap definition will give us a preset color gradient from dark blue to white. Next, we fill in some of the parameters to help with understanding the visualization. In this case, we'll use the standard collection 0 from Seaborn for our color bar. This will just give us a preset gradient color bar, which saves us a lot of time from having to code our own colors on a color bar. Next, we'll set the color bar ticks to 0 through 3 and label those ticks according to our 4 strike levels: severe, heavy, scattered, and mild. Lastly, when we code the show function, we are given a beautiful heat map. Using the heat map, we can find the most severe lightning strike months across all 3 years. Thanks to Pandas and Seaborn, transforming data into categories and back into numerical data is possible with just a few lines of code. As we discussed, it's easier to plot a visualization by using strike level code as the base values. The categories we created of mild, scattered, heavy, and severe became the labels on our heat map plot. Labeling coding can be as simple as that, and it is an essential skill for data professionals. When I think about input validation and the EDA practice of joining, I like to think about vegetables. Allow me to explain. When you're at the market picking out leafy greens and root vegetables, you check that they're fresh first, right? And not just at the store. You also check on them at home when they're in the refrigerator. Plus, you probably ensure that they're still edible one more time before you cook and eat them. Lastly, if for some reason the vegetables have gone bad or you didn't buy enough for a recipe, you would need to add more. Performing EDA on a dataset is similar to checking for the freshness of vegetables. You are searching, exploring, and checking that the data is as error-free as possible. You should check and recheck your datasets to make sure that they are correct. As I mentioned before, as a data professional, you should know your dataset thoroughly. One way to make sure you know a dataset is validating it, which is, as you recall, one of the 6 practices of EDA. There are many different ways to validate a set of data, but here we'll discuss input validation. Input validation is the practice of thoroughly analyzing and double-checking to make sure data is complete, error-free, and high quality. Input validation is intended to be an iterative practice, meaning you should perform it again and again in between and during the other 5 practices of EDA, which are discovering, structuring, cleaning, joining, and presenting. Most often, as a data professional, you will perform input validation when starting a new analysis project or getting familiar with a new data source. We will discuss more about the how of performing input validation later in the program. Now, we will focus on the why and the what. Why should we take the time to validate data? What exactly are we looking for? When we validate data, we help make more accurate business decisions, and we improve complex model performance. Think about it like this. If a gourmet chef doesn't double-check the vegetables for freshness before cooking a dish, the food could taste horrible, or worse, make people sick. It is much the same with data. The more careful we are in checking and rechecking our data after each manipulation of the data during EDA, the less likely we are to have problems later. Clean and validated data can help prevent future system crashes, coding issues, or wrong predictions. So, while we are performing our validation work, what is it that we're searching for? No 2 datasets are alike. There will be different things to check for based on the type. Here are some questions to consider when validating data. Are all the data entries in the same format? For example, are people's ages expressed as solitary numbers like 23 and 47, or within a range like 18 to 35 and 35 to 50? Are all entries in the same range? For instance, in finance, are some of the values expressed in thousands of euros and others in millions of euros? Finally, are the applicable data entries expressed in the same data type? For example, are all the dated entries expressed in the same format of month, day, or year? While asking these questions, or while performing EDA in general, you may find that the data you have been given is not sufficient to answer the business questions that you have been tasked with. For example, let's go back to the comparison we made earlier in the video to a gourmet chef and his vegetables. Imagine that the gourmet chef is introducing a new recipe to their restaurant. They're not sure how many vegetables will be needed for the new dish. In the end, the chef realizes halfway through that day that they did not account for additional vegetables to be used in vegan and vegetarian dishes. It is at that point the chef would buy more vegetables. The EDA practice of joining is much the same principle. As you've learned, joining is different from the structuring technique, merging. While asking these questions, or while performing EDA in general, you may find that the data you have been given is not sufficient to answer the business question. Joining is the process of augmenting data by adding values from other data sets. The practice of joining will be most useful if we validate the data to ensure formatting and data entries align and are the same data type. For example, while adding the new vegetable, the chef will want to make sure the consistency and taste are similar to the vegetables that they've been using all day. Otherwise, the dish may not turn out the same. You will need to use your own logic, common sense, and experiences to understand the ways in which you should join or validate each particular data set you work on. There won't be a rigid process to show you down to the detail how to handle each data file. Data science takes a lot of analytical thinking and shifting of perspectives to be thorough in your EDA and validation. Experience and effort will be the best way to improve your performance in analytical thinking. We'll also be exploring examples in our Python notebooks as well. Keeping your validation practices in line with the PACE workflow will also help you keep a focus on ethics. Validation should be about cleaning and correcting data for the sake of quality and correctness. You probably won't be surprised to learn that the EDA practice of validating fits squarely in the analyze phase of our PACE workflow, but is also a practice you should use for all 4 phases. Remember, PACE stands for plan, analyze, construct, and execute. This means that what and how we join and validate data should be in alignment with the plan phase of the workflow. For example, if your task is to discover which week within a given month is most profitable for a business, it will be important that you check and recheck that you've grouped the revenue dates into weeks correctly. Your analysis won't be effective if you think you've grouped revenue by week, but actually done it by day or month. When you look to validate your data to this level of detail, it will help you toward meeting your PACE goals, specifically for the construct and execute phases. Before we end, there's one more thing that can help you with validating and joining aspects of EDA. Look to your peers and managers to help you. A peer-reviewed dataset is one of the best ways to ensure that you check yourself on bias, keep ethics as a focus, and ensure you are on track with the PACE workflow. Remember, validating data is like checking your vegetables to find if they're the right choice for the recipe. It may take extra time up front, but it may save you from headaches and stomach aches down the road. In this video, you'll perform input validation in Python. Remember, input validation is the practice of thoroughly analyzing and double-checking to make sure data is complete, error-free, and high quality, just like checking your vegetables before you cook them. With that knowledge fresh in your mind, it's time to discuss how to perform input validation in Python. We'll focus our validation on the NOAA data for lightning strikes from 2016 to 2018. The goal will be to check for errors and prepare this dataset for publication. Let's open our Python notebooks and get started. First step, as usual, we will import the Python libraries and packages that we need for input validation. You'll notice we have pyplot from matplotlib, pandas, plotly express, and seaborn. Next, with our lightning strike data libraries and packages all imported in our notebook, let's use the head function to take a look at what we have in terms of columns and the top 5 rows. You'll find our familiar lightning strike dataset also includes a 4th and 5th column, longitude and latitude, respectively. If we were to check the data types now using df.dtypes, we would discover the date column is a string data type. As we did previously, let's convert the column to date time. One thing we should include in our input validation is a check for missing data. You'll recall from earlier that we likely will have already done this check for missing entries during the cleaning part of EDA. The definition of validate assumes an action or process has already been completed. So if we input is null.sum into our notebook in order to give us missing values for the second time, it is a practical and not redundant thing to do. After running the code, we find that there are indeed no missing values. Next, for this dataset, let's review the ranges of all the variables. In this review, we will check the highest and the lowest values of each column, the earliest and latest dates, and the overall distribution of values. To do this, we'll use the describe function, which you may recall from a previous video. In the argument field, we'll use the parameter includes equal all. This will tell the notebook to include every parameter covered by the describe function. You'll notice NaN values in some of the describe fields like unique, last, and max. Remember that these are not fields in the dataset, but rather a summary table of attributes. For example, you'll notice that there are NaNs in the date column for mean, min, 50%, and max. These are to be expected because dates are not data types that would be averaged. Speaking of dates, let's double check our date column. First, are there any calendar days missing? We know from prior EDA work on this data set that the date column should include every day of each year. Let's confirm each day is listed by designing a calendar index. We'll call it full date range. We'll then use the pandas date range function with the first and last dates of 2018 in the argument field under the start and end parameters. After that, let's add full date range dot difference. Then, in the argument field, we'll add df and in the brackets, the column header date, which will limit this function to checking only the date column. The result is interesting. There are 4 consecutive days missing in June of 2018, then 2 consecutive days in September, and 2 consecutive days in December. This finding would be something to investigate or to question the owner of the data to find out the reason why. Working as a data professional in a business setting, you would want to repeat the same process for the other 2 years as well. Given that the number of missing days is relatively small, you could complete your analysis by making a note of the missing days in the presentation. This will ensure that anyone who analyzes your visualization or presentation will know that the data depicted doesn't include those missing dates. Now that we've done some initial validation, let's get a better sense of the range of the total numbers of lightning strikes. If we use a simple box plot data visualization with number of strikes as our data parameter in the argument field, we'll find that the distribution is very skewed. Most days of the year have less than 5 lightning strikes, but some days have more than 2,000. As you recall from a previous video, we can remove the outliers from the box plot visualization to help us understand where the majority of our data is distributed. We can do that by adding show flyers equals false into the argument field. The result is much easier to interpret. It shows us that the biggest share of lightning strike values fall between 5 and 13. From what we know of lightning strikes in the North America regions of the United States, Mexico, and the Caribbean, this distribution is conceivable. If the highest distribution of strikes were all in the 2000s, we might be a little more skeptical. The last bit of input validation we will do is to verify that all of the latitudes and longitudes included in this dataset are in the United States. This will ensure we don't have any mistakes in our geographic values. To do that, we'll first create a new data frame that removes all the duplicate values. We'll type df underscore points equals df, then latitude and longitude in double brackets. Following that, we'll add dot drop underscore duplicates. The reason we want to drop duplicate points for the latitude and longitude is that we don't need to check a particular location on a map twice. After running that code, we have a new data frame that only includes 2 columns, latitude and longitude. Within those 2 columns, we find that there are no duplicate data points. Finally, we will plot these points on a map. Here's a tip. When you're working with hundreds of thousands of data points plotted on a map, it takes a lot of computing power. To make it a shorter runtime, we'll use the Plotly Express package. The package is designed to keep runtimes as low as possible. To plot these latitude and longitude points on a map, we use the scatter geoplot from Plotly Express. Within the argument field, we'll fill in the proper parameters for a scatter geoplot. In this case, we'll first input the data frame name df points, followed by first lat for latitude, then lon for longitude. And the last code is to show the scatter plot. After running the cell, you'll notice the runtime is still slow because of the sheer volume of the data. But we do see very clearly all of the latitudes and longitudes fall within the United States. You'll find that during the EDA process, there will be times when you need to add more data to your dataset. As we've discussed previously, adding new data columns from other sources is called joining. You may need to join new data at any point during EDA, but often it will come during the discovering or validating stages of your data. Thanks to Pandas and the other Python libraries and packages, adding more data to datasets is a very straightforward process. Let's revisit our notebook and try it out. For this exercise, let's add the 2014 and 2015 data to our original 2016 to 2018 lightning strikes dataset. To start, convert the date column from data frame to date time, just like you did for the 2016 data. So our new data frame, df_2, will input first, followed by the column header date in brackets. Next, we'll use pd.toDateTime with df_2 and the column title date placed in the argument field. Running the head function will confirm that our new data frame looks like we expect. Next, our task is to add the same columns of latitude and longitude to our new data frame that we have in our original. Python joining functions work best when all of the columns match up, both in format and in total quantity. Lastly, we'll create one big data frame putting all 5 years together, 2014 to 2018. We'll call this data frame union_df. Then we'll use the pandas function merge to align the columns of the two data frames. Finally, we'll use the head function to understand the results of our coding. Most data professionals use input validation regularly, so these are important concepts to learn and important technical skills to practice. As you learn, datasets can be busy and chaotic. There are many different things happening in them. It can be difficult to figure out where to focus and how to uncover those stories buried beneath the surface. In this section of the course, you learn some important strategies to help you correct mistakes and discover hidden data stories. We focused our story finding efforts by learning the EDA practices of cleaning, joining, and validating. We discussed a lot of ways to engage in those practices. We focused on working with missing values and outliers, transforming categorical into numerical data, and input validation. And we reminded ourselves not to forget to visualize our data in Python to help further our understanding. We discussed identifying missing data and outliers in Python and why it's important, both from an ethical perspective and a business sense, to find them. We considered the difference between categorical and numerical data and why transformation using Python is important. As for input validation, you learned what it is, why it's important, and how to perform it using Python. We also discussed some workplace skills along the way, such as understanding when to communicate with stakeholders or other subject matter experts about missing values. We also reviewed ethical considerations you should make when performing cleaning, joining, and validating work. You learned why these practices are vital when performing EDA on a dataset as part of the PACE workflow. EDA can be an exciting process. Thorough EDA not only saves time and energy on future processes, but it also helps you find the trends, patterns, and stories in the data. Later, you'll learn how to use Tableau to design and present data visualizations to key stakeholders and business managers in a business setting. In the meantime, you've learned some amazing skills that data professionals use almost every day. The ability to perform careful EDA on a dataset in Python is an essential building block in a data professional's career. Great job on your work so far. We've reached the final practice of EDA, presenting. As we discussed, visualizing and presenting don't necessarily come at the end of your data exploration. You may create visuals of your own data throughout the data analysis process. The practice of visualizing your data will help you discover insights and further your own understanding. The presenting practice of EDA is an important part of both the analyze and execute phases of the PACE framework. Sometimes you'll create visualizations to analyze the data during the analyze phase. At other times, you'll utilize data visualizations as part of executing an algorithm. In this video, we will focus on designing data visualizations for the purpose of presenting. In this course, we'll discuss concepts such as accessibility, Tableau basics, dashboards, and data visualizations. You may recall some of these concepts from the Google Data Analytics certificate. If you'd like, take a few minutes to review that content before moving ahead. Coming up, you will learn how to improve your data visualization skills. The accurate representation of data is one of the most important aspects of a successful presentation. You'll learn specific techniques for making data visualizations that represent the data with precision. Another aspect of designing successful data visualizations is ensuring they are inclusive. We will talk about tips and techniques for making your data visualizations accessible to a diverse audience. You will also learn about the data visualization platform Tableau. Tableau is a versatile data visualization software primarily used for presenting data to inform and improve businesses. Using the software, you'll learn how to create data visualizations that tell stories and explain technical concepts to non-technical audiences. You'll learn to create dynamic visualizations with interactive and motion elements and to alter visualizations based on different audiences' needs. We will also discuss how to choose the right graphic or chart, give context during presentations, and select the proper order and timing for your data visualizations while presenting. Data professionals often need to create data visualizations and deliver presentations. That's why we'll discuss the most important skills to help you thrive in this area. After all, you want your audience to understand your data story. As a data professional, you will have an opportunity to tell data-driven stories that change your team, department, company, industry, or even the world. Now let's get started. Often, creating a data visualization is an iterative process. The first graph you design may not be the one you share with stakeholders. The colors, text, labels, scale, and areas of emphasis are all aspects of a graph that may change to meet different business needs. But how do we get to that final product? What decisions should we make along the way to create a successful visualization? To answer these questions, we'll take a sample data set and create a data graphic. Then, we'll discuss how to alter the visualization along the way. This will illustrate the types of decisions data professionals make when creating graphs and charts for presentations. Now let's get started. Imagine you're working on a new app which will gather a list of the top-rated rental homes and apartments in Europe in one easy-to-access place. Your company asks you to start by gathering the best rental listings in Athens, Greece. You want to know the locations of rental units where the owners have 40 or more property listings. You only want properties with many good reviews and a rental listing price between 90 and 250 euros. This helps to clarify the type of visualization you need. Since you want the locations of rental units where owners have 40 or more property listings, you need a geographic map. Additionally, you limit the count of listings based on the criteria of your analysis. To create a map with the locations of rental properties, a program like Tableau will be the most effective. If you're familiar with Tableau, feel free to add this dataset into the public Tableau and try it yourself. First, we'll start with a map of Athens. We'll plot all the rental listings on that map. We'll use filters to remove rental properties that don't meet the analysis criteria, such as prices outside our defined range. Finally, we'll adjust the formatting to make our map easily understandable and accessible. Let's consider the dimensions of the graphic. We know that the end result needs to be a map of listings in Athens, Greece. Let's input the latitude and the longitude from the dataset and plot those listings with the host name as the labeled spot on the map. Now that we've added those data points to Tableau, let's see what it looks like. We have a map of Greece. but we need to refine it so that it is easier to read. Next, let's filter the listings we don't want based on our analysis criteria. Narrow the results to only those owners who have more than 40 rental listings. We can do that with the column in the dataset called Calculated Host Listings Count. We limit the amount to only values over 40. This narrows the fields. Next, we limit the entries by price. Our criteria includes listings between 90 and 250 euros, which gives us a much more manageable number of listings. We want to keep only the listings with a lot of reviews. The word a lot, of course, is relative, so we'll use a percentile filter to just give us the top 50% of total reviews. This is the result. Now we have a reasonable amount of data points. But what's next? We need to make it easier to comprehend. To do so, we add a title and add a color coding for the owners of each listing. We also add the price for each listing, and this is the result. At this point, we have a workable visualization that meets our criteria. This is a successful first version. However, if we want to make this visualization part of a formal presentation, we need to make it accessible. We do that by including a descriptive caption beneath it and making the marks slightly smaller so more of the price is displayed. We also want to be sure the colors are friendly to individuals who might have difficulty seeing color. This is the result. The goal with visualizations is to meet an audience's needs. You want to share the geolocation of rental property owners. You accomplish that with your map of Athens. But what if the app's business team decides they need different data displayed? Or if you want to review property listings by neighborhood, you would need to update the visualization. The main point here is that the resulting visualization may not always fit the business need. Designing visualizations, as you'll remember, is a multi-step process. Even after you've completed a visualization, you will sometimes find you need to update it. You may also get new information that requires you to change the original criteria. Making changes and fixing mistakes is all part of the process. We talked a lot about the power and usefulness of Tableau. Are you ready to log in and try it out? Great. We'll discuss how to access a free online version of public Tableau, build basic data visualizations, and understand when to use a variety of charts. You may remember some of these concepts from the Google Data Analytics Certificate, and you can revisit that program for a quick refresher. When you access Tableau Public, it may appear different from this video. Keep in mind that Tableau Public may have updated its user interface. This should not be a problem because the steps you follow are almost the same. To begin, go to the public Tableau website, which is the free online version of Tableau you can access from your browser. Sign into your Tableau Public account. Next, you'll need to access a new data source in Tableau Public. We'll use the NOAA Lightning Strike dataset again for this video. On the Tableau Public homepage, select Create a Viz. Upload your data source from your computer using the file provided for you. Once the data is uploaded, you will be redirected to Tableau's Data Source screen. The dataset is divided into 4 columns: date, number of strikes, x-coordinate, and y-coordinate. There are symbols above or to the side of these fields' names representing the types of data that are included in the dataset. There's a calendar icon for the date, a pound sign for the numeric column, number of strikes, and globe icons for the latitudes and longitudes, or x and y coordinates. There are also tabs representing a new worksheet, new dashboard, and new story. Create a new worksheet. A worksheet in Tableau Public is a data page that contains a single view of a data visualization. The new worksheet is blank other than the data column. The data source field of the worksheet is preloaded with the column headers we identified on the data source page. There is a thin line separating the list into 2 sections. This indicates the data type and whether the data is discrete or continuous. Tableau divides all the data fields into two broad data types, dimensions and measures. You can tell them apart based on the icons Tableau assigns to each field. Dimensions are qualitative data values used to categorize and group data to reveal details about it. Measures are numeric values that can be aggregated or placed in calculations. The green and blue colors in Tableau indicate another aspect of the list of dimensions and measures in the Tableau Worksheet Data tab. Green indicates that the data field is continuous. Blue indicates that the field is discrete. The term continuous is a mathematical concept indicating that a measure or dimension has an infinite and uncountable number of outcomes. Discrete is a mathematical concept indicating that a measure or dimension has a finite and countable number of outcomes. With these definitions, we can learn about our list of data fields even before we plot them on a chart or graph. Keep in mind that Tableau may assign the wrong data type. You can always change data from measure to dimension or discrete to continuous by right-clicking on the data field if the data type and its label do not match. Next, let's begin our visualization by plotting a line graph. Line graphs are useful for presenting time series data or tracking changes in data values over different periods of time. To start, drag date into the column field. In the pop-up that displays, you can select different segments of time. Select year for this chart. Next, drag and drop number of strikes into the row field. You now have a line graph. Now, you know how to create line graphs. Next, we'll create a bar chart. Bar charts are useful when you want to compare things like data from two different time periods. To get started, use the toolbar to duplicate your worksheet. In the New Sheet, open the drop-down menu in the Marks field. Select Bar. Changing data visualization types is really that simple. Next, let's create a bar chart to compare two data sets. Go to the Filters tab and edit the filter. Check 2009 and 2018. Leave all the other years unchecked. You'll find a comparison of the total number of lightning strikes in the years 2009 and 2018. Next, add a label to each bar by dragging number of strikes to the square in the Marks field titled Label. Now, we know the exact difference between the number of lightning strikes in 2009 and 2018, 30.1 million and 44.6 million, respectively. For the last visualization, let's compare 2009 to 2018 by quarter. To start, duplicate the worksheet again. Drag date to the column field. Tableau will automatically add quarters to the stacked bars, sectioning out Q1, Q2, Q3, and Q4 for both years. To make the side-by-side comparison of each quarter stand out, drag date to the color square in the Marks field. The colors will adjust based on the year, with 2009 in the original color and 2018 in a different color. You can keep the chart like this, or click the drop-down arrow and select quarter instead. Now the quarters are segmented by different colors. To determine the color scheme, decide if you want to highlight the differences between quarters or between years. You're starting to discover how useful Tableau can really be. Often, data professionals use Tableau for their EDA work because it helps them quickly create visuals of their data. Soon, you'll be able to do that too. So far in this program, you've learned the basics of Tableau Public, like how to upload a data source and use discrete or continuous measures and dimensions to plot data visualizations. Next, you'll design more complex visualizations, including heat maps, box plots, and histograms. You'll also learn how to input calculations and write code within the design elements of a visualization. Let's get started. Go to Tableau Public and create a new data visualization. we'll use another dataset from the NOAA lightning strike data. Once you've uploaded the data source, you'll start your data visualization on the data source page with the NOAA lightning strike data. The date, longitude, latitude, and number of strike columns are all there. Let's open a new worksheet so that we can create a geographic map. This requires latitude and longitude data that Tableau can use to plot the points. First, drag longitude from the data list to our columns field. Next, drag latitude into the rows field. Now, we have a map. This is a great start. Next, filter the data so that you have fewer data points to work with. Drag date into the filters field and select year from the dropdown. Then, configure the filter to select only the year 2018. Next, use color gradients to help differentiate the denser locations on the map from the more scattered lightning strike locations. Drag number of strikes to the box labeled color. In the drop-down menu under marks, make sure that density is selected. Now that the map is much better, the default color for this visualization is blue. The lighter blues indicate more scattered lightning strikes, and the darker blues are heavier lightning strike areas for the year of 2018. To change the color, click on the color square and change it from automatic to just something else. Try one or two. Consider which will make the map most accessible for yourself and for people who might have visual disabilities. Next, let's create a heat map. As discussed in a previous video, a heat map is a type of data visualization that depicts the magnitude of an instance or set of values based on two colors. To create a heat map in Tableau Public, you need one or more dimensions or one or two measures. To start, drag date to the row field and select year. Next, you need to create a calculation that derives the month from the date string. In the Date drop-down menu, click Create and select Calculated Field. A pop-up will open. Let's give the calculator a title. For the calculated field name, input month. Use the left function to pull the month names from the string in the column Date. Pull the first three letters from the month listed in the string, type left, parentheses, date name, parentheses, month, in single quotes, a comma, date in brackets, parentheses, a comma, and 3. Then add a closing parentheses. Click OK. Now, there is a new field on the list of data on the left. Drag month to the columns field. Then drag number of strikes to the color square under the marks field. Be sure that in the marks dropdown, that square is selected. Now, you have a heat map. Just like the density map, the default color for this heat map is blue. You can adjust the heat map to a color range that fits your needs. Remember to consider accessibility as you create your visualizations. Now, let's create a box plot. You'll recall from a previous video that a box plot is a data visualization that depicts the locality, spread, and skew of groups of values within quartiles. You've already learned how to create a box plot chart in Python. To create a box plot in Tableau Public, first drag date to the row field, then drag number of strikes to the columns field, and select year. If Tableau doesn't default to box plot, select circle from the drop-down menu under the marks field and scroll to the Show Me tab to select box and whisker plot. What you have so far is not much to look at. All you're seeing is a thin line of data points in a blank field of white background. However, once you drag date into the detail square under the marks field and select day, you'll see box plots appear in full strength. With box plots, most data pros will include a legend or annotation of the exact numbers of median and mean for presentation. You can, of course, change the colors and size of the circle in this box plot using the color and size squares under the marks field. Our last complex plot is a histogram. A histogram is a data visualization that depicts an approximate representation of the distribution of values in a data set. To create a histogram, first, you need to create bins. A bin is a Tableau term that describes the custom segments of data that values can be grouped into. Bins are an important part of histograms because the groupings in heat maps determine how the data is segmented and compared. For a histogram of lightning strike data, group the total number of lightning strikes into bins. Do this by clicking on the Number of Strikes dropdown. Select Create and then Bins. You can give the bin a name and then determine the size. If you select 50 for the size of bins, there would be one bin for every 50 lightning strikes. Any value between 1 and 50 would be included in that bin. Because there are millions of values of lightning strikes, you should select a number between 5 and 10. This will display the distribution of values in much more detail. Next, drag the new bin to the columns field. Then, drag number of strikes to the row field. Make sure the number of strikes in rows is the count, or CNT, rather than sum or average. This presents the actual count of each bin. To give us more detail, drag number of strikes to the filter field and limit the field numbers between 1 and 200. Drag number of strikes to the label square under the marks field. Make sure it is set to count. You can adjust the color to make the data visualization more accessible. Coming up next, you'll learn how to create a series of data visualizations to use in a presentation. I'll meet you there. Data professionals often need to present their data. Creating, sharing, and discussing data visualizations is an important part of telling data stories. In this video, you will create a series of data visualizations that work together to tell a story. This will allow you to lead an audience from one concept to the next and build additional context as you present each visualization. But first, let's consider a scenario. Imagine you're working for an organization that wants to learn more about lightning strikes in the United States. They request a series of data visualizations that illustrate the increase in lightning strikes over time and detail lightning strike data in 3 states: Texas, Oklahoma, and Kansas. After you create your visualizations, you will need to share them with the organization's directors. With the audience in mind, you can get started. You need to consider 3 strategies for organizing and presenting data visualizations in a series: chronological, generic to specific, and specific to generic. A chronological approach to data visualizations is useful for data that is best understood in a time series. A generic to specific approach helps an audience consider an issue before describing how it affects them. And a specific to generic approach is useful to highlight impacts the data can have on a broader scale. Let's select an approach. A chronological approach, or time series, would be most helpful to consider data over time. This does not address an important aspect of the request: visualizing strike data in 3 specific states. With a specific to generic approach, the climax of the presentation would focus on the United States as a whole rather than lightning strikes in Texas, Oklahoma, and Kansas. This does not meet the needs of the organization. A generic to specific approach would allow you to illustrate the country-wide increase in lightning strikes, followed by specific data on each state. You can highlight national trend before targeting the lightning strike data in Texas, Oklahoma, and Kansas. This meets the organization's needs, so a generic to specific approach is the best choice. Before you design your visualizations, you need to create 3 different Tableau Public worksheets. These will form a story in Tableau Public. A story is a Tableau term for a group of dashboards or worksheets assembled into a presentation. For the first worksheet, you will create a line graph showing an upward trend in lightning strikes over 3 decades starting with 2009. For the second worksheet, you will show that the greatest amounts of lightning strikes have shifted from the east coast of the United States to the south central mainlands over 3 decades. And for the third worksheet, you'll show the number of lightning strikes in Texas, Oklahoma, and Kansas in 2018. the last year with complete data. These 3 sheets will form the generic to specific organization for the story. Let's open Tableau Public and start designing. As always, start by uploading your data source. For the column field, drag in date, which is a discrete dimension, and select year for it. And for the row, add the number of strikes measure into that field. A line graph should appear. If it doesn't, open the Show Me tab and find the Lines Discrete selection. You'll notice the line moves steadily upward from 2009. Next, we will make the data visualization easier to interpret. For example, add 2 annotations to the line graph. First, add 30.1m strikes in 2009 to the beginning of the graph to give the audience a clear starting point. Then add 45m strikes in 2018 to its applicable position. Next, let's create a geographic data visualization. Since we want to progress from generic to specific, it is important to show the trend of lightning strikes moving west over the decades. To do that, we needed to create a time series map that shows the location of lightning strikes in the US for each year since 2009. In the new worksheet, place the x-coordinate in the column field and the y-coordinate in the row field. This will create a map focused on the eastern and central US. If you're still seeing a line chart, make sure that both your x and y coordinates are marked as continuous. Once you have the geographic map, click on the drop-down for both the x and y coordinates and select Measure, then Average. This will give us a manageable view of the average number of lightning strikes in the US for each year. Next, add the date discrete dimension to the filters and the pages fields. Select Year for the filter method. The filter field allows us to create a dynamic filter which can be used to select just 1 year of lightning strikes. The pages field can create a distinct snapshot or page of lightning strikes for each year. Finally, add the number of strikes to the detail field. The map showing lightning strike locations is comprehensive. We just need to add the interactive part to it. With the year dimension in the pages and filters fields, you can format interactive legends to the side of the data visualization. These allow users to self-select the years they wish to see. We have 2 of the 3 worksheets done that we need for our presentation. The last thing to create is the most specific visualization of the 3, a snapshot of 2018 lightning strikes for Texas, Oklahoma, and Kansas. To do this, we'll create 3 new worksheets, 1 for each state. Then, we'll place the 3 snapshots into 1 dashboard. We'll work together on the Texas visualization. Then, you can create the Oklahoma and Kansas visualizations all on your own. Our map of lightning strikes in the state of Texas starts in almost the same way as the geographic chart we just made. We put the x-coordinate in the column field and the y-coordinate in the row field. We put the number of strikes measure in the detail field. This time, we add number of strikes to the color field and make the color coincide with the number of strikes. Use red for most strikes and yellows for fewest. Because we will limit these state snapshots to just 2018, we drop the date into the filters field, select year, then uncheck all the years except 2018. Finally, we need to create a set in Tableau Public. A set is a Tableau term for a custom field of data created from a larger data set based on custom conditions. We can create a set by first selecting all the data points in Texas. To do this, we'll use the lasso tool. You will follow the state line as best as you can all the way around Texas. Once complete, you'll find a pop-up window. Select Keep Only, then click Create Set. Drag your newly created set to the filter field. Now, only the average lightning strikes for Texas will show up on our map. We can now assemble them into one story. First, add the 2 other state worksheets for Oklahoma and Kansas, which were created in the same way as the Texas worksheet. Then, create a dashboard for the 3 states illustrating the locations of lightning strikes in the US for the year 2018. You should also create dashboards for the other 2 worksheets created earlier, the line chart and the interactive map of the US. Now that we have 3 dashboards, we can create a story in Tableau. On the first page of the story, insert the dashboard with the line chart. Fill in the caption to give details about what the chart is showing. On pages 2 and 3 of the story, put the interactive map of the US followed by the dashboard that includes all 3 states, Texas, Oklahoma, and Kansas. With the 3 captions filled in, we have a complete story. Coming up, you'll learn how to create an interactive dashboard in Tableau. I'll meet you soon. So far in this program, you've been practicing essential Tableau skills. Now, you will learn how to put these skills together and create an interactive dashboard. The interactive dashboard you create will display the quantity and the location of all lightning strikes in the United States from 2009 to 2018. The dashboard will be color-coded based on the quantity of lightning strikes, and it will allow viewers to select any year or location to learn the count of the strikes. Let's get started. Begin by opening Tableau Public and uploading the data source provided. To build the dashboard, you'll need to create 3 different worksheets. First, you'll create an interactive US map with locations of lightning strikes for each year. Then, you'll create a dynamic stat sheets listing the metrics for each year. Finally, you'll design a way to pull and display the lightning strike metrics for the individual locations on each year's map. Let's start with the interactive lightning strike map. To begin, add the x-coordinate and the y-coordinate in the column and the row field. Next, drag date into the filters field and select year. Make sure the show filter option is checked. For the last part of this map, drag number of strikes into both the color square and detail square in the marks field. The color square will categorize the dots on the map with a color code based on the quantity of strikes. The detail square will plot the locations for each of the lightning strikes for each year. Make sure when you do this that both number of strikes variables are set to continuous. For the next worksheet, you will create a list of 3 metrics that will change on the dashboard whenever a year is selected. The 3 metrics are total number of strikes, average number of strikes for each location for that year, and maximum number of strikes in any location. This worksheet will differ from our other visualizations. It will be text rather than a bar chart or line graph. It will sit to the side of the interactive map and update whenever a new year is selected. First, create a calculation from the number of strikes dimension. In the blank field space, type number of strikes and put it in brackets. Next, drag the new calculation into the tooltip square in the marks field. In the drop-down, select measure and average. Repeat this process, but instead of selecting average, you should select sum and maximum. This creates dynamic fields for 3 metrics: the total number of strikes, the average number of strikes for each location for that year, and the maximum number of strikes in any location. Finally, create a place to display these calculations. To keep it simple, go to Worksheet and select Show Title. Input the title, Metrics for the Year. Under that, you will include the 3 calculations in the tooltip. To do this, put an asterisk followed by total, colon, and then sum and number of strikes inside the left and right angle brackets. Repeat this step for the maximum and average tooltips you created. And there you have it. For the last worksheet, drag number of strikes to the text square in the marks field. In the drop-down, select measure and average. This creates a dynamic field for the dashboard we'll create next. Now, select New Dashboard. You should find all your worksheets in the list on this page. Drag over the worksheet with the interactive map in it. It may take a few seconds to load. Next, drag your other two worksheets into the dashboard. Before we clean these up, we need to create an action for the dashboard. An action is a Tableau tool to help a user interact with a visualization or dashboard by allowing control of a selection. When a year is selected from the filter bar, all the other fields will update with it. We will connect the three worksheets together with an action. Click on the map in the dashboard, select Worksheet and Actions. In the Actions pop-up, select Add Action and Filter. In the Add Filter Action menu in the Source Worksheets section, select your dashboard from the drop-down. Check the box for your map, and for the Run Action On list, click Select. For target sheets, select your dashboard from the drop-down. Then select the map and the recently completed worksheet that will gather metrics for individual locations. From the list of clearing the selection will, select Show the Values. Lastly, select all fields for the filter section. Click OK. And now you have an interactive dashboard. Update the text and titles before you're done. Add a title to the filter legend, Interactive Filter. You should also title the location average variable, Location Metrics, and write brief instructions to clarify what the tool does. For example, you might type, choose a point on the map to view location-specific metrics. Take a few minutes to test your dashboard. Select different years and locations on the map to make sure the tools function properly. What a collection of Tableau skills. The tools and techniques you've learned in this video will help you communicate and present ideas more effectively throughout your career as a data professional. Good luck and happy designing. If you were to design a data visualization of what you've learned in this program, what might it look like? Would you plot your engagement level over time on a line graph? Or would you create a heat map showing the tasks you completed with different colors representing the tasks that took the least and most time? No matter what visualization you choose, you've learned the skills you need to create an effective graphic or visualization that an audience can understand. You've learned to use Tableau Public to tell your data stories and to adjust the content depending on the audience. We also discussed the best ways to share technical concepts with non-technical audiences. You learned to use Tableau at a high level, and you've applied the technique data professionals use to create visualizations. No data visualization discussion would be complete without considering ethics and accessibility. You learned that as a data professional, it is your responsibility to ensure visualizations accurately represent the data. You also learned how to make data visualizations accessible for people who have visual impairments. You learned a lot. Congratulations on completing this section of the program, and good luck on the rest of your journey.
Hi, I'm Tiffany, and it's great to be with you again. You've made a lot of progress in the program, so I'm back to tell you more about your portfolio projects and how you can use them in your future job search. Remember, your portfolio will be a collection of materials you can use to showcase your approach to solving data-oriented problems. In the portfolio project for this course, you will demonstrate your knowledge of telling stories using data. It's an incredibly important skill for a data professional to know on the job, but it's also critical for success in an interview. As potential employers assess you as a candidate, they might ask you for specific examples of how you approach cleaning, structuring, and validating data in the past. You can use your portfolio as a way to discuss actual data challenges you have resolved and real stories you have presented. Additionally, some employers might ask you to create a presentation based on a data set they provide. The skills you've learned in Python and Tableau to create data visualizations will help you feel more comfortable and prepared for those interviews, as well as build out your portfolio. You already learned about experiential learning, which is when people gain understanding through doing. Watching an instructor create a visualization is one thing. Creating a visualization yourself to expand your understanding of the concepts and improve your skills at presenting to stakeholders is another. This portfolio project is also a great opportunity to discover how organizations are using data analytics every day and show off your knowledge of how to tell data-driven stories. To complete the portfolio project, you'll be working with a database and an accompanying business scenario. You'll use the instructions to complete a Jupyter notebook showing your EDA work and 3 to 5 visualizations in Tableau in response to the scenario. By the time you complete this project, you'll have a comprehensive presentation you can add to your data professional portfolio. In your PACE strategy document, you'll also have documentation of the steps you took along the way, which you can use to explain your work to future hiring managers. You're almost finished with this course, which means you're advancing your understanding of what it means to be a data professional. Now it's time to demonstrate what you've learned. This portfolio project will help you practice and demonstrate the skills you've learned throughout the course. For example, you'll be able to show how to perform the practices of EDA in Python. Using Tableau, you'll demonstrate how to create data visualizations that accurately detail a dataset story. And you'll be able to demonstrate how to prepare and document a comprehensive workflow strategy using PACE. Ready? Let's go. In this course, you've been learning about using the 6 steps of the EDA process to tell stories with data. Now it's time for an exciting next step, putting all this to work for your portfolio project. In the previous course, you learned the basic formatting and structure for writing code in Python. These coding skills will be critical to the completion of your next portfolio project, which will require you to clean, analyze, and present data to technical and non-technical audiences. Now that you have some practice completing portfolio projects, think about how to reframe the data you're analyzing and cleaning it into a well-thought-out story. In this part of the course, you'll take a dataset and apply the 6 steps of EDA to formulate a useful document that can help you present key findings to stakeholders. In other sections of this program, you will work to develop additional skills to help you thrive in the data career space. There's so much more to learn about telling stories with data. As a data professional, a large part of your job is focused on transforming messy data into an organized, clear story that meets business goals and helps stakeholders understand important details needed for making business decisions. This portfolio project is a great opportunity to demonstrate to potential employers that you can do exactly that, turn messy data into a logical story. And remember, developing your skills as a data professional is an iterative process, so you can continue to improve as you have new ideas or learn new things. At this point in the program, you've done a lot of work toward better understanding data and how it can be useful for enacting change in a business. You completed a Jupyter notebook, created visualizations to support your work, and refined your presentation to meet the needs of your particular audience. As you continue to make progress in this program, remember that documenting your learning, process, and skills will help you communicate what you've done to potential employers and hiring managers in future interviews. You may recall from previous sections of this course that audience awareness is essential. During the interview process, knowing how to talk about your work process, transferable skills, and other achievements will lead to much greater success. In this course, you learn the importance of following the PACE structure in a data career. You practice using Python to manipulate data, and you demonstrated how to organize and analyze a set of data to tell a compelling story. The portfolio projects were designed to help you thrive on the job market, and the transferable skills you applied contributed to the tangible artifacts you created. As you begin preparing for future interviews, you should be ready to answer questions like, what is your process for cleaning data? What tools do you use for creating data visualizations? How and why do data visualizations enhance the stories data tells? And what considerations are top of mind when sharing data stories with non-technical stakeholders? Of course, there may be many other questions that you are asked as you interview for a data professional role. Each portfolio project will help you prepare responses. For example, in the portfolio project you just completed, you use the EDA process to clean, organize, and analyze a dataset. Then you turned your data into a presentation full of visualizations that will help stakeholders understand insights from the data story you discovered. Don't forget that you recorded all of your considerations, questions, process notes, and more in your PACE strategy document as well. Coming up, you're going to learn all about the power of statistics in data-driven work. Then you'll have an opportunity to use statistical analysis to simulate an A/B test. By the end of these courses, you will have lots of artifacts in your portfolio.
Do you remember imagining yourself as an archaeologist at the beginning of this course? You stood in front of an ancient riverbed at dawn, excited at the possibilities of what you might find under the rock. What stories would you uncover? What long-lost mysteries might you reveal? After learning the content in this course, hopefully you've had the same level of excitement an archaeologist feels when it comes to EDA and visualizations. As you've learned, the 6 practices of EDA help find the stories that need to be told from datasets. As you're discovering, structuring, and cleaning in your career, I hope that you are digging through the data with determination, gathering your major finds together, questioning your perspective, and researching more about your discoveries. Then, I hope you remember the other 3 practices of joining, validating, and presenting to complete your EDA work. In this course, you've had the chance to explore how data professionals take care of the stories that have plot holes or puzzling scenes, or that is, missing data and outliers. You also learned how to change categorical data into numerical data using the label encoding technique. And finally, you considered how to design visualizations and present your data in really impactful ways. You learned the advanced concepts of visualizing, and you started using Tableau. Throughout these lessons, you learned some workplace skills like communicating to different audiences, the importance of ethics, the need for accessibility, and the importance of following the PACE workflow. These are the types of skills which will serve you throughout your career, from entry-level data professional to senior data professional and beyond. In the upcoming courses, you'll be learning some integral concepts in statistics, regression, and machine learning. The knowledge you've gained in our course will be foundational to your progression through these next courses, as well as through your career as a professional in data analytics. It has been my pleasure instructing you. The practices of EDA and data visualization are close to my heart, and I'm always excited to meet future data professionals learning these principles. Great job on completing this course. You have the makings of a solid storytelling data professional. May you always find excitement in exploring and telling stories using data.